Yeah, I'm done.
Okay, let's go ahead and get started then. So thank you, welcome back. Our first speaker of this afternoon session is Alfredo Guevara. He's a physicist. He received his PhD from the Perimeter Institute this year and joined us at Harvard as a junior fellow in the Society of Fellows. He's going to tell us from higher spins to gravitational waves in Kerr. Yeah, thank you.
Great, great. Well, first of all, let me thank you to the organizers for this amazing conference and also the opportunity to be here. So I hope we can meet in person in the coming year. So I wanted to tell you about some project I've been working for some time now, but this is somehow the most recent update. So I'm gonna review some of the background and then introduce you to what are the latest results. So the project is titled "From Higher Spins to Gravitational Waves in Kerr Backgrounds." Um, so let me start with two problems that you might have heard of in gravitational physics and also in high energy physics. Okay, so on one side, we have perturbations of the Kerr black hole. So there's a lot of interesting phenomena going on here. We have superradiance phenomena for bosonic perturbations. We have quasi-normal modes. We would like to compute quasi-normal modes analytically. We would like to get Lyapunov exponents analytically. These are also important for merger processes. We have the classical process of absorption and the quantum process of Hawking radiation. We have there is a recent puzzle about whether spinning black holes do have vanishing love numbers, so the analog of electric and magnetic susceptibility. So there are many problems which, for us physicists, we would be interested in get some analytic progress in these directions. Okay, and this is of course aiming to applications in terms of binary black hole problem as well, and templates for gravitational waves. Okay, so on the other hand, there is also an interesting problem which comes from very old days in the development of the S-matrix program, which is the question of interacting higher spin particles in quantum field theory. Okay, so we know, for instance, that string theory predicts an infinite number of massive higher spin modes. So we believe that this is not an accident, and string theory, in a sense, what it's doing is satisfying certain unitarity and causality constraints that are supposed to emerge in any consistent theory of quantum gravity. Okay, so if you write down an effective field theory, an effective theory for quantum gravity, you can include, for instance, R square operators. You can include Lovelock terms, and so on. You will find that in order to satisfy certain unitarity constraints of this theory, you are required to include a tower of higher spins states. Okay, and we're going to briefly review how that goes. This is an argument by Maldacena and company. But let's just say that higher spin states, they are known as bond states, so they can emerge. They are not fundamental. So there are hadronic states which are spins 3/2 and higher. We know that these are not fundamental, but nevertheless they occur in nature. Okay. So I wanted to propose, and I want to introduce you to a new link between these two problems. Okay. And the link is as follows: the Kerr black hole. Okay, so in gravitational physics, can be identified with a consistent higher spin particle, which is coupled to gravity. Okay, and this claim has been developed among this reference here, but now we have some more detailed understanding on how that works. So in a sense, there is a solution to this interacting higher spin problem, and I wanted to somehow convey to you that is actually given by the Kerr black hole. Okay. So so let me just introduce the link. So let's consider a 3-point amplitude. Okay, so the 3-point amplitude, you see here some incoming momenta. Okay, there's some incoming momenta which is massive. There is some massless momenta. Okay, so that I'm gonna interpret as some graviton coupling to some massive state. And my claim is that I can consider two states here, A and B. So I have some higher spin states, A and B, some polarizations. And I find that this amplitude, I can write it as an exponential, okay? The exponential, of course, is an operator. The operator here is the standard Pauli-Lubansky operator. So this carries the spin of the massive particle. So there's this nice exponential structure that appears in this amplitude. And we can interpret that as some intrinsic feature of the Kerr metric. Okay, so I take this massive particle, this massive 3-point amplitude, and I compare it with what I know is a very close form of the Kerr metric. So I write down the linearized a linearized perturbation here, carrying out the Kerr metric, and this comes some projection operator. I write down the spinless part, okay, of the Kerr metric, and I can write this as some kind of boost acting on the spinless part, which is just the Newtonian, just the Schwarzschild piece. So there's A dot del here acting, as you can see, on this 1/r component. Okay.
So, sorry, Alfredo. What was your starting point for the exponential there? How did you get that formula? You're assuming it. You're going to derive it.
Yes. Good. I'm gonna get you through it in a second. But let me just say for now that we can write down this amplitude and it makes sense, and okay. it makes sense for any spin. Okay, that's all I'm claiming. Okay,
you're so just I can defining this amplitude. You're not saying it describes anything in particular.
Yes. I'm just defining, and I'm claiming it's consistent. And at 3 points, basically, there is no much there's no more constraints that you can impose. So there is this simple amplitude, and I claim that there's a correspondence between that and the Kerr metric. So the Kerr metric, you see, it has this A dot del parts. So this is some kind of shift operator. And if I go to 2,2 signature, you can write it. You can solve certain constraints, and it turns out that you can combine this cos and sinh into an exponential form. Okay. So you have to pick a choice of sign. It's the same choice of sign that you have to do here when you decide the helicity of the gravity. So what this means, okay, that it means that this amplitude, what it's telling you about, is about the radiation modes corresponding to this metric, right? So graviton only carry the radiation information. And of course, in Minkowski signature, Kerr black hole is stationary, so there's no radiation. But if I go to 2,2 signature, I can actually get these radiation modes, and this is what this amplitude is encoding. Okay, so I just wrote down a graviton amplitude, and I'm claiming that it has the information of the Kerr metric. Okay.
Does a radiative mode in 2,2 analytically continue to a Coulomb type or a
yes
mode in 3,1?
Yes, but the amplitude vanishes because you can see here, amplitude only has support on radiation mode. So yeah. if you look at this delta function has no support. So that means that there is no radiation. But yes, so you can continue, of course, the structure of the amplitude to the Coulomb type. Okay, so this is just to give you a flavor that the scattering amplitude provides a natural derivation of what is called the Newman-Janis shift, introduced in the 70s and so on. That really the Kerr metric is nothing but some kind of shift of certain components of the Schwarzschild metric. Okay, and this shift is precisely the exponent of the exponential. Okay. Okay, so that's the 3-point amplitude story. Now, Andy asked how do I derive this 3-point amplitude if I don't know about the Kerr metric? And the way I derive it is by a criteria called the minimal coupling criteria. You can take any massive amplitude, but if you go to the high energy limit, there is only one choice that's going to give you the correct massless amplitude, the correct 3-point massless structure, okay? So and this is what I call the minimal coupling choice. And this minimal coupling choice is important because it has been shown in some old papers that at lower spins is equivalent to no superluminality. So if I write down the equations of motion of this massive particle, okay, this massive higher spin particle, imposing that there is no superluminality, no causality violation, according to these people here, will tell you that you need a high, well-behaved high energy limit. Okay, so this is how we pick up, we select. This is some kind of super selection rule for this 3-point massive amplitude. And on the other hand, this massless amplitude is actually unique. So it was shown in this paper by Cachazo and Benincasa that there's only one 3-point structure for this particular helicity combination. So if I have helicity plus S and helicity minus S, so S here was previously the spin, but now it's helicity of the massless particle, and I have a graviton of plus or minus 2 helicity, there's only one thing you can write down for this structure, okay? So in a sense, this is completely unique. I didn't know anything about the Kerr-Plakov, but using just this minimal coupling criteria, I know what's the 3-point amplitude that has the information of the Kerr metric, okay? But now we want a consistent theory of higher spin particles. We want a consistent theory of higher spin particles, meaning we need to compute any multiplicity amplitude, okay? So not just 3-point amplitudes. And that's where the problem starts. So massless 4-point amplitudes, okay? So the 4-point amplitude, the 4-point analog of this amplitude, it's inconsistent. There is no way of making an interacting theory of massless higher spin states. And there's a problem with unitarity, so it doesn't factor correctly on these 3-point objects. So really there's no criteria for minimal coupling, okay? So we don't have this criteria now at 4 points, but now we can ask the question, of course, what is the 4-point amplitude that matches the Kerr-Plakov, okay? So in a sense, I show you what's the 3-point amplitude, but no, there's no criteria, so I want to know what's the 4-point amplitude, okay? Now, in order to answer this question, so what's the 4-point amplitude? We need to go a little back in history and recall what is the Reye-Wheeler equation, okay? So we consider the Reye-Wheeler equation, which governs the perturbations of the Schwarzschild metric, okay, so no spin, with certain helicity. It can be 0, it can be a scalar perturbation, electromagnetic perturbation, or a gravitational perturbation. Also, there is these neutrino perturbations. And we write down this equation. You see there is some potential here that depends on the helicity. And it also depends on L, which is the angular momentum, is the orbital angular momentum of the perturbation itself. And the perturbation itself is encoded in this, the so-called Newman-Penrose scalar. So the Newman-Penrose scalar is just some scalar that encodes this perturbation. And the angular dependence is given in this spin-weighted spherical harmonics. So these are some generalization of spherical harmonics introduced by Newman and Penrose and so on. The thing we care about is the radial dependence, and the radial dependence is what enters this Reye-Wheeler equation, okay? So this is our starting point. So we want to study perturbations of Schwarzschild for now. But we want to study those for a quantum mechanical framework. So instead of looking at this just as some perturbation of Einstein equations, I'm gonna look at it as the Schrödinger equation. And if I want to understand it in terms of the Schrödinger equation, I find that we need to do some scaling, okay? So we need to introduce some H bar. And the scaling is such that you scale the frequency with H bar. So your quantum mechanical frequency, the frequency of your particle, scales with H bar. The radius, some kind of impact parameter of your particle, scales with 1 over H bar and so on. And you keep this gentleman here fixed, okay? So this means, in particular, that the Schrödinger equation that I'm going to propose can access the physics of the Reye-Wheeler equation only in this long wavelength limb, okay, where omega of the particle is really small because it scales with H bar. And that's going to tell you that, okay, the lambda, the long wave of the wavelength is going to be much bigger than the actual Schwarzschild radius. So that hints you that there's going to be some particle interpretation of the black hole. Okay, so that's the whole goal of this. We want to think of black holes as fundamental particles of higher spins. Okay, so now I tell you there is some Schrodinger equation if I do this scaling. But now I can do second quantization, and I can replace, instead of solving the Schrodinger equation, I'm going to compute an amplitude in quantum field theory. Okay, so I can replace this source, which in this case is the black hole, by some massive particle. Okay, and this agrees. These two agrees if I take some non-relativistic limit, which is already encoded in the h bar to 0 limit. So really, these are the same in this limit. So just to show you how it works, I write down the Schrodinger equation. Okay, so I want to study scattering in the Schrodinger picture, and then just write down an incoming plane wave, and then some outgoing scatter wave. And we use the Born approximation, so we plug in some form of the potential here, and we just keep the lowest order in the coupling constant, and we find this. So H here is precisely the metric sources by the black hole. Is the potential, is the H mu of Schwarzschild. And we solve this equation, so it's some Helmholtz equation. We solve it in the long distance limit, and we find that the amplitude, the scatter wave, okay, the scatter wave is given by some kind of Fourier transform of the Schwarzschild metric, contracted with the momenta of my scalar here, right, of my scalar wave, okay. And this I interpret as, okay, I'm taking some Schwarzschild metric, which is some background field. In momentum space, I'm doing this Fourier transform. This is sourcing certain momenta into my scalar. And I'm just computing this 4-point scattering, okay? And this is the vertex for the massless scalar, okay? So I have massless scalar, the Schwarzschild black hole, some momenta going on. And you can see this dependence here. So there's some Coulomb, some Coulomb force acting on the amplitude, and that's actually gonna be reflected on certain phase, which is gonna appear in the outgoing wave. So the outgoing wave is gonna have what's called the Coulomb phase. It's a standard in long range forces. I can comment more about that if you wish. Okay. So we know now that we can replace 4-point amplitudes. We can solve this Rayleigh-Wheeler equation by just computing this 4-point amplitude. So we can extend this dictionary, and instead of solving the Rayleigh-Wheeler equation, we can solve the Teukolsky equation. So that means include a spin in your computation, so non-zero spin. So instead of Schwarzschild, you do Kerr. You replace the spherical harmonics by the spheroidal harmonics. So there's some dependence on the spin now. Okay, in angular components. And instead of plugging a massive scalar in the 4-point amplitude, okay, a massive scalar in the 4-point amplitude, I'm gonna plug a massive higher spin state, okay? And because the spin is a quantum number, it's gonna be large when I take the classical limit. So really I'm gonna take S to infinity, the spin quantum number to infinity, okay? That's the analog of the classical limit. So I'm gonna compute the very same 4-point amplitude, but instead of plugging a massive scalar, I'm going to plug a massive spinning particle. And instead of plugging a massless scalar, so that's the wave, I'm going to plug a massless particle of the helicity that I want, which is 0, 1/2, 1, or 2 if I look for gravitational waves, okay? So this is going to be reproducing the same computation as classically solving the Teukolsky equation. And this is the amplitude. You can see there's some incoming momenta, P, some helicities of two gravitons or scalar waves or electromagnetic waves and so on. Notice that K1 and K2, they have this frequency dependence. And as I show you here, the frequency has to scale with H bar. So really our scattering waves are given, their momenta is given by this omega times n and H, and it scales as H bar, okay? So really, this is going to be some soft process. Okay, so by setting the incoming massless momenta to some reference, and we have some angular dependence on the outgoing massless momenta, we can very easily expand this 4-point amplitude into partial amplitudes. Okay, so that's really just some technical just some technical process, and we match these partial amplitudes with this Newman-Penrose scalar. Okay, so it's not easy to compute the 4-point amplitudes. Okay, it's just single Born type exchange diagram. Okay, so this is just some exchange diagram, and I know the 3-point information because I know already what is this 3-point vertex here. I showed you at the beginning, and I just glue that with some helicity H wave. And there's momentum transfer, which is K2 minus K1. So you can also see that it scales as H bar. So let's just do it. And we compute, for instance, for a scalar wave. So we put a scalar here. This is the answer, okay? So you can see that it has some exponential structure in the spin. And this part, the scalar part, is basically just the so-called Rutherford cross section. Okay. In particular, it has this divergence as theta goes to 0. So theta here is the scattering angle. If I look at just the spatial components of in and out massless momenta, there is some scattering angle in there, and the amplitude is going to diverge where the scattering angle is going to 0. Okay. So this is just because of the long range nature of the gravitational interaction. But there is some conclusion that I can already give you, which is that the other helicity choice, okay, so here notice that I'm looking at plus helicity going to minus helicity. Actually, if I flip the momenta, because this momenta is outgoing direction, is outgoing direction, this is preserving the helicity. So this is going with plus helicity and going out with plus helicity as well. So the helicity of this massless particle doesn't change. If I compute the other choice, okay, where the helicity flips, I get 0, okay? And I get 0 basically because of the soft theorem that tells me that if I have a soft graviton here, the helicity of my matter particle is gonna be conserved, okay? So in this case, I have the soft momenta because this momentum transfer scales with the frequency, which is h bar. So the helicity of the helicity of the massless wave is conserved. That means that in the scattering in the Kerr black hole, in the Kerr background, in this regime, there's helicity conservation. Okay, as long as this is the only diagram contributing. Okay, so if I take a photon of plus helicity and I scatter that, so the photon has some circular polarization, for instance, I scatter that with the Kerr black hole in the long wavelength regime, it's gonna have still the plus helicity. Okay, the only exception is if it's in the gravitational wave scattering. So if this guy is a graviton, there are more diagrams that contribute, and that's why gravitons can flip helicity. Okay, so there is a helicity violation in that case. Okay, but even though in these cases helicity is conserved, there is some interesting phenomena going on here, which is polarizations. So if I have non-zero spin, okay, so suppose I throw an incoming wave with plus helicity or minus helicity. If I have a non-zero spin, what I'm gonna find is that the amplitudes, okay, so the amplitudes that I already computed, these 4-point amplitudes, are gonna be different for plus or minus helicity. And that's telling me at the very end that the scattering angles of these two dudes are gonna be different, okay? So that's gonna polarize my beam of light or whatever beam I'm throwing at it. And the way I can measure this is, of course, by computing the difference of these two scattering angles for both helicities at fixed impact parameter, okay? And this is given by roughly is the difference of these two amplitudes. So I have one amplitude with plus helicity and the other one with minus helicity. And these two are related by complex conjugation. So this is parity being implemented here. And because of the spin vector is a pseudo vector, it flips sign under parity. So orientation flips. And that means that I have to flip A. And because of that, the difference of these two amplitudes is gonna be controlled only by odd terms in the spin. So in particular for Schwarzschild, there is no difference. Okay, these two terms are gonna be the same and there's no polarizations. Okay, so I can compute it explicitly I solve for theta scattering angle in terms of impact parameter, and I find that there is some function here b to the cube. That's the impact parameter. A large impact parameter. This is the first leading correction, and you see it's odd in the spin. Okay, so really this tells you that only because of the effect of the spin in this case, there's going to be some polarization induced. And this just follows, as I said, just from the parity conjugation of the scattering amplitude, and at the very end, that's just crossing symmetry at work. Okay, so that's just some application of the correspondence. Now, before I run out of time, how much time do I have?
About 5 minutes.
Okay, that's enough. I wanted to just briefly mention the unitarity constraints that we can derive from this correspondence. So if I take the scattering angle to 0, I'm going to see that independently of the helicity of this wave, I'm going to get the same amplitude at the leading order in the scattering angle. Okay, so the amplitude is going to depend on some component of the spins, AX and AY. But it's not going to depend on the helicity. So this can be gravitational wave, it can be a photon wave, or any other wave, as long as it's massless. And there's this universal behavior, okay? So we also know that this function really doesn't depend on parity. So if I compute the other parity, so the parity conjugate version, you remember here, we have to conjugate and flip the spin. If I compute the other helicity, this function is invariant. Okay, this is even in the spin, this is odd, but there is an I here, so it cancels when I complex conjugate. And really, at this order a leading order in the conal approximation. Okay, so really scattering angle, the limit where the scattering angle is small, there is no polarization. And this has a very, very simple explanation, which actually unveils a whole new framework to work with these constructions, is that in this limit, in the theta going to 0 limit, this scattering amplitude is controlled only by geodesic motion. And the mapping between geodesics in the Kerr black hole and the scattering amplitude is not a trivial map, so it has to be carefully derived. But I'm just going to give you the answer, okay? And the answer is I take the scattering amplitude, okay, as a function of the momentum transfer, of the exchange momentum, and I Fourier transform this in some two-dimensional Fourier transform, okay, so just in the scattering plane, I Fourier transform to impact parameter space, okay? When I Fourier transform that, I find that the amplitude has this form. Okay, this can be derived, it follows from unitarity constraints, but it's always true, it's true in quantum mechanics and it's true in quantum field theory. This actually has an exponential structure, okay? This is true at all loops and so on. So this is a general statement. And this chi here is what's called the scattering phase. And from the scattering phase, basically I can derive all the classical information that I need in terms of geodesics and orbits of the Kerr black hole. Okay, so what this is in the classical perspective is roughly the radial action of the Hamilton-Jacobi formulation of geodesics in Kerr background. Okay, because of that, these are basically Hamilton-Jacobi equations, and I can just derive the scattering angle from the Hamilton-Jacobi equations by varying this with respect to impact parameter, and I get some function like this. This is precisely what you get if you just compute geodesic in the equatorial plane of the, if you just consider geodesic in the equatorial plane of the Kerr black hole. This is precisely the scattering angle you get, and you can compute time delay as well by varying with respect to the energy of the wave. Again, using the Hamilton-Jacobi equations. And what you find, at least for this polar case, which is here what I advert, this is a warning, okay, that we're only looking at aligned configuration. So really the spin of the black hole is aligned with the spin of the wave, with the moment of the waves. If you look at this particular case, you find that you can very much compute this time delay analytically, and it's positive. Okay, so that's a unitarity constraint. There's no causality violation. You have a time delay, as expected. So this has to be positive. Here B is an observer at large impact parameter. Okay, so that brings me just to the conclusion. So in the conclusion, I want just to mention 3 things. So the first thing is that we have seen how the scattering of waves in the Kerr black hole is completely contained in these 4-point amplitudes of quantum field theory after some classical prescription is implemented. 2 things that you should be skeptical of is that there is some Coulomb dragging force. So really you need a little more than 3-level amplitudes, but nevertheless this Coulomb dragging can be implemented. Okay, there are no free asymptotic states in 4 dimensions, but there is a simple way in which we can incorporate them in this picture. So at the very end, we only compute these 4-point amplitudes. The second one is that for gravitational wave scattering, there are more diagrams, okay? Because gravitons interact not only not linearly, but also they couple to the source. If the source is gravitating, as it should be, really you have 3 more diagrams, so the computation is more extensive, and it's not enough with the 3-point information that I gave you, okay? There is lots of new and interesting results in this direction, but I didn't have time to explain what happens with this gravitational wave scattering, but it follows from this construction. Second conclusion is that polarization effects are just consequence of the parity of scattering amplitudes. And third, and maybe one of the most important ones, is that higher spins in this picture as matching, as obtained from this analogy or this correspondence to the Kerr black hole, are indeed defining a consistent interacting quantum field theory in this classical limit. And by consistent, I mean that the time delay is a positive, which is a reflection of the unitarity in the approximation I showed you. Okay, so that's it. Thank you.
Okay, thank you. So we have a number of raised hands in the audience. So let me just start with Avi. Do you want to go first?
Thank you. Thank you, Alfredo, for an excellent talk. You know, many decades ago, there was a suggestion that perhaps some elementary particles are black holes. Can you shed any light on how we would be able to tell if there was some really point-like particles that they have a metric similar to a metric of a black hole around them? From scattering experiments, that's what I'm asking.
Yes, that's a good question. So from scattering experiments, you may suspect that black holes are bound states, so they have quasi-Norman modes and so on. But from the study of the S matrix, we can look at bound states as well, because these are singularities in the S matrix. Okay, so we compute scattering, we define this matrix, and there's some singularities in the complex plane that we interpret as bound states. So one direction that we're currently exploring is understanding these bound states in order to derive quasi-normal frequencies. And so that would be a hint that there is some black hole structure more than what I showed already, which is already non-trivial. But in order to see things like Hawking radiation and so on, we need to understand these singularities.
Thank you.
Shahar?
Yeah, thanks, Alfredo. I wanted to ask, so when you're calculating the leading diagram for a process like quasi-normal modes or something else, you're basically getting the first order in G Newton, right? It's like in an expansion in G Newton of the quantity that you're computing.
Yes.
So do you have an idea like how close this approximates the full, like, for example, if you want to calculate like time delay or deflection angle you can calculate that to all orders in G Newton for geodesics and Kerr, right? And then you can
Yes,
compare.
yes, yes. Yeah, it's a very good question. So the keyword here is a Conner. So in the Conner approximation, which is basically given by a scattering angle, a small scattering angle, what we find is that the full, let's say, non-perturbative amplitude, okay, is dominated by this kind of ladders. And if you resum these ladders, in the Conner approximation, because there's very small momentum transfer, the ladder resummation factors in some way that you get an exponential, okay? So really, when I'm talking about the Conner approximation, I'm talking about all orders in G Newton. And that's how it was shown by people in the 90s, and first by Tuft and then by Ortiz and Cabat, that the Conner approximation encodes the spectrum. And it encodes not only the spectrum, it encodes the bound states and as you said, the time delay and so on at all orders in G Newton. Okay, so you can think of this as just being some certain geodesics in the Kerr black hole. Sorry, here one of these guys is the massless guy. So I should say one of these guys is Kerr and the other guy is massless, okay? But the limit is the same. So momentum transfer small, and I see that this whole infinite sum just resums into some exponential function. And that's precisely the scattering phase that I wrote down.
Alex? Alex, you're muted. Okay, let's go to Andy.
Yeah, my question, I guess, related to both Avi and Shahar. So you're not seeing any, well, you're certainly not seeing any black hole microstates, right? So you're working in an approximation where the particle can't go in and right and change, and that's also related to, you know, deformations of the geometry of the surface of the black hole. You know, those are described according to the membrane paradigm by some kind of thermodynamics, and they know about the microstates. So now, but so why does this approximation? So it would seem that, like, if you ever want to see the Hawking radiation, as you were discussing in response to Avi's question, well, maybe that one doesn't need microstates. But you're not including any back reaction, right, on the black hole? You are, you aren't?
Yeah. No,
you're allowing part of it to back react, but not others?
We are not so far, but we can compute we can compute more diagrams than this. So yes, at tree level, which is what I'm doing so far, really there's no back reaction. But I believe that if you start computing things like, so far we have been computing things like this. I believe that if you start computing things like this, okay, so there is some back reaction effect. Okay, it's just that this is sublink in this long wavelength regime. So remember that we are looking at the regime where the frequency, the wavelength of the graviton is much bigger than the Schwarzschild radius, but this is a sublink correction in that regime. Okay, so it should know about absorption.
Well, let me put it this way. Your diagrams where you have a particle come out and the black hole go on, you allow the mass in this, you allow the spin of the black hole to change, but you certainly don't allow the microstate to change. You just, your diagrams aren't rich enough to do that, right? You would have to have some other internal state. And in principle, well, so we know that there are exponentially many of those. And they become important in many classical processes. In the thermodynamic limit of those exponentially internal states become important, and I think in properties that have been astrophysically measured by this point. And so why is it what is the approximation that enables you to neglect that exponentially large degeneracy?
No, we're not. If you look at this part of the while loop diagram, this actually has quantum amplitude inside it, right? So this actually contains all. So you have two gravitons. I'm just looking at this side, right? So
yeah, but the initial black hole and the final black hole, the quantum state could be different, which would give you, I don't know how many. Yeah, so you would have exponentially many possibilities, consistent with. Your calculation is giving the right answer, so there must be some reason why you could do this. But it would be nice to know when it's okay to neglect that and when it isn't.
Yes, yeah, I don't have the answer to that question yet. But what I can tell you is that we believe that when we compute this quantum amplitude, which we haven't so far, there are many higher spin states propagating in this channel. Okay, so this is something you don't see at tree level, but it's something that you can see at one loop level.
Polynomially many in the spin.
Well, you have an infinite series of spherical harmonics, so it can be infinite. There's an infinite series of spherical harmonics which are higher spin states, and that may know something about what you're talking about.
Well, that's nowhere near the black hole degeneracy, right?
Infinitely many, but yeah, okay. I should think about it. Okay, yeah, maybe we can talk about it later.
I mean, it's working, so there must be a reason. Also, this business about the love numbers.
Yes.
But it would seem that is that known from GR point of view or just from this? I would have thought those love numbers have something to do with transitions between microstates, because
yes. So love number is not known in GR and it is not known anywhere. So really, this is still an open question whether spinning black holes have vanishing love numbers. And one answer, so one way to answer that question would be to look at this process. And people actually did look at this process, but it's still very confusing how to match that to the love number computation. But I agree that's one direction.
Thank you.
Okay.
Okay, let's thank the speaker again, and we will now move on to our second speaker of this session, Paul Tiede.
I just need to share my screen. Oh, there we go.
We don't see you, by the way.
Oh yeah, let me turn on my video. Sorry. There we go. Right. Can everyone see my screen?
Yes.
Yeah.
Okay, perfect. All right.
So you're all set?
Yep.
Okay, we're very happy to have Paul Tiede joining us today from the Perimeter Institute and the University of Waterloo. He's going to tell us about variational image domain feature extraction and modeling the horizon.
All right, so thank you. So yeah, so this is going to be a little less theory heavy than the previous talk. So what I'm mostly going to focus on is modeling with the Event Horizon Telescope. So just as a reminder, the Event Horizon Telescope is a global radio array. And so by having a bunch of radio dishes throughout the planet, and actually we have one on every major continent except Australia, but by doing this, you can basically turn the entire Earth into a radio telescope. And so because of that, you actually get enough angular resolution, as I'm sure you're all aware, so that we are able to image the image of a black hole. And so that's this I guess now famous image here that I actually grabbed off Wikipedia at this point. If you're on Wikipedia black hole page, you see this image. But what I'm going to talk about a little bit more in this one is actually how we do some modeling with the EHT. And there are really two different methods. There's a non-parametric or imaging method, and then there's a parametric model. And this talk's going to kind of be broken up into two distinct chunks. And in the first part of this talk, I'm going to talk about the non-parametric or imaging methods, and more specifically, some feature extraction tools. And so why do we need a feature extraction tool? Well, it turns out that if you're doing imaging, it's really only the first step. And so what imaging methods do is that they're extremely flexible, and so they don't assume any a priori source structure on the sky. And so in this sense, you're not fooling yourself or biasing yourself to hopefully see into the image that you expect to see. The downside of this is that if you try to actually extract some physical information that you're interested in, such as the diameter of the black hole or its position angle of its bright region, you need an additional processing step. And furthermore, you have to apply this processing step to thousands of images. And so by doing this initial processing step, this feature extraction, you're able to move from your image to some parameters of interest here. The problem with the methods that were used for the first EHT results is that they baked in an assumption that the image was dominated by a ring, and these methods don't apply to like other source structures. So for instance, if you have an image that doesn't have a ring-like structure, such as the EHT image of 3C279, your pipeline that you've developed to extract these features of interest no longer applies, and you'll have to go through an entire new process again. And so what I've developed with some collaborators is a technique called VIDA, or Variational Image Domain Analysis. Its paper actually appeared on Archive this morning. And it's a general image feature extraction tool. And the idea behind it is that you can approximate some truth image here with some simple parameterized model. So some like geometric ring, for instance. And then what you can do is similar to the match filtering type idea in that LIGO uses, is that you can extract the filter that best matches your ground truth image. And then using that best filter, you can learn something about the image sky. So something like the brightness distribution or the asymmetry or the diameter of the ring. And the nice thing about this is that because you just need a simple parameterized filter, you can actually generalize this to any image features. And so what this actually means is that the features in your image that you're interested in are in a direct correspondence with the filter you used. So if you have some image reconstruction of some source that looks like this, if you just want to get a diameter, you can pick just a filter that has some ring diameter. But if you want to add more features like a slash, you can just implement a new filter that incorporates those features. And in fact, you can add multiple filters, so you can extract subdominant features, or even filters with strange azimuthal profiles if what you're really interested in your image is why are these lumpy structures. And so what we've done so far with VIDA is actually we've shown that we can reliably reconstruct reconstruct features from images from some of the test images in the first EHT results. So these are some imaging tests that are from paper 4 in the first EHT results. And so you have a crescent image, a couple crescent images at a couple different position angles, and a GRMHD image. These are some example reconstructions running through the EHT pipeline. And then this is what VIDA says is the best fit filter. And so VIDA is able to at least reliably capture some of this source structure. But the nice thing is that VIDA doesn't just apply to these ring-like images, is that you can actually apply it to other image structures too. And so, for instance, if your image looks something more like 3C279, so example like this Gaussian double, VIDA can also reconstruct these by just picking a Gaussian double filter. And using this, we were able to reconstruct the correct brightness ratios, the positions, and everything. But one of the big reasons that we developed VIDA was actually to apply it to some of the M87 images and to better understand some of the things we saw in the M87 images in the first EHT results. And one of the things we noticed was that across all 4 days, the ring looked a little asymmetric. So across every day, you had this asymmetry parameter, which is 1 minus the semi-minor axis over the semi-major axis. And you can see every one of these has some positive measure of asymmetry. And what we wanted to understand was, where is this asymmetry coming from? Because this asymmetry could, if it's something physical or real, it could be saying something interesting about the source. And so to do this, though, we can't just look at the asymmetry. What we actually have to do is we have to calibrate this. And so we have to calibrate the expected asymmetry that we see to just the theoretical spread you would expect just from uncertainty in your GRMHD simulation. And so this is similar to what we did in actually the first paper results. And similar in the sense that what we actually got out of imaging was just the diameter of the black hole. So we found a ring, and it had a diameter of like roughly 41, 42 microarc seconds. But this doesn't actually relate to the parameter of interest that you're actually after with the black hole, namely its mass. And so what we had to do is we had to calibrate this mass to, we had to calibrate this measured diameter to the mass of the black hole. And to do that, we had to fit a number of we had to run an image a number of GRMHD simulations with the exact same pipeline that was used to create this, and then find this this alpha parameter, or this scaling relationship between the measured diameter and the actual black hole mass. And what happened was that this calibration is added an incredible amount of uncertainty to our mass measurement. So our actual diameter measurement was given by this blue line here, but after we folded in all of the observation, or all the theoretical uncertainty from these GRMHD simulations, our error bar is increased by like an order of magnitude. So that's going from these solid lines to these dashed lines. And what we actually have to do is we have to do this again for asymmetry. So we have to do a calibration for asymmetry, just so to know how much asymmetry we would just randomly expect to occur. And so the first step we wanted to do, or to check how well our array could measure this asymmetry, was doing a very simple test. And so what we did is we had a number of asymmetric Gaussian rings. And then what we did is we imaged each Gaussian ring using the same imaging techniques that were used in the first EHT results. And what we wanted to check was whether the current imaging results could actually recover this asymmetry, and whether it could cover this asymmetry across a wide variety of position angles. And what we found was that it really depended on where the semi-major axis of that asymmetry was. So for instance, if your semi-major axis was in the north-south direction, the imaging methods did a pretty good job at recovering an asymmetric ring. The recovered asymmetry found by VIDA matched the ground truth. And this is also similar for this 135 degrees and 45 degrees. However, when the asymmetry was aligned in an east-west direction, we found that the imaging techniques used in the first EHT results actually hid away all the asymmetry, and it just looked like a circular ring again. And so what this suggested is that there's some combination of image asymmetry and the baseline coverage, or the sensitivity of the EHT array. And so what this means is that the imaging methods used likely couldn't detect, or were not very sensitive to at least in 20% asymmetry. And this is even before we actually do the GRMHD calibration. If we try to do a GRMHD calibration, where we image an entire GRMHD library, run it through the EHT image generation suite, so going from these images here to these images here, and then fit VIDA to it to try to cover the asymmetry, what we find is that the asymmetry is largely unconstrained, and it can actually, the asymmetry in the image reconstructions can actually grow up to about 40%, and depending on its where it likes to put the orientation. And so what this means is that these imaging methods likely aren't very sensitive to actual intrinsic asymmetry in the source, in the sense that they can hide asymmetry and they can also add asymmetry. And so what this means is that this calibration factor that we need when moving from our measurements to our actual theoretical uncertainty is quite large. And so we're not going to be able to, and so any asymmetry that you see with these image reconstructions is likely artificial, or just due to the imaging methods themselves. And so what this really gets to is actually just a general problem with the imaging and feature extraction pipeline that I just talked about. The problem with imaging is that what we actually do is we're just trying to fit the image on the sky, and what we're actually ignoring are the deep physical processes that generate those images. So for instance, for a black hole, there's not just some ring on the sky, but instead there's an accretion disk and there's emitting material around that accretion. There's emitting material from that accretion disk, and as it leaves that accretion disk, it travels around the black hole, and that's how you get the ringed image. And these imaging and feature extraction techniques know nothing about that. They have no way of knowing what the accretion flow looks like, its velocity profile, or the properties of the local spacetime. It just knows there's some ring on the sky. And to go from that ring on the sky to actually the physical parameters that we're interested in, like the mass, we need to do this calibration step. But this calibration step is highly uncertain and is really up to the fidelity of our imaging techniques and fidelity of our imaging techniques. And so what we would actually like to do is model not the image on the sky, but model actually the model around the horizon. And so for instance, here's a number of GRMHD simulations, and what we're looking at is a cross section, a vertical cross section of where the emitting material comes from. So most of the emitting material we see here is actually for certain simulations is in this region here. And what we'd actually like to do is model this. So model what the emitting region looks like. If you can model that, you can include a number of physics that modeling the image can't, such as the space-time and the accretion flow parameters. And so one of the simple ways that we can try to do this is actually to approximate the accretion flow with some simple semi-analytic models. And this goes back to some work actually a couple decades old from Ramesh and Avery Broderick and Hung-Yi Pu. And what these are is that you approximate your accretion flow with some simple phenomenological models, such as the electron density of the accretion flow looks something like a power law. It has some characteristic height, h. It has some characteristic accretion flow, something like a Keplerian flow with maybe some inflow parameter. And what you can see is that just with these very simple construction, you can construct a wide family of different accretion flows. So as we change the height, you can change whether the disk looks like this spherical kind of blob with a small hole to if a much thinner disk, you can really start seeing the photon ring start to pop. But one of the questions is this accretion flow actually, is this simple model flexible enough to describe an accretion, to describe what we actually see? And so what we actually see is something more akin to this GRMHD simulation, where you see a whole bunch of filamentary structures orbiting around the black hole, and it's quite time variable. And now, of course, if we actually saw this, or we had enough resolution to see this, the RIAF wouldn't be quite flexible enough. But that's not what we actually see with the EHT array for a few reasons. One, the EHT array is incredibly sparse, so the image is intrinsically kind of blurred, but also specifically for Sagittarius A star, the black hole at the center of our galaxy, it actually gets blurred by a scattering screen. And so what we actually see on the sky is something more like this. And then once you add in some refractive substructure from the scattering, it looks like this. And so we don't have to do, the RIAF doesn't have to reproduce this, it just has to reproduce something that looks closer like this. And what we find is that if we fit a RIAF to these GRMHD simulations using the coverage that we have with the current EHT array, we actually find that the quote best fit RIAF to this simulation looks very close to the average GRMHD image. So this is the, and even better than that actually, is that it actually does a reasonable job at recovering the parameters that you want. So for instance, the M/D, the mass of the black hole is a little bit larger than or the mass of the RIAF is a little bit larger than the ground truth, which is shown in blue, but it's much closer and there's less calibration that is needed with the imaging methods. Similarly, we were able to get a slight measurement on spin, and as well constrain what the inclination of the black hole was. And so just by doing a very simple phenomenological model, we were able to extract a lot more potential information of what the actual source looks like. But we can actually even do a little bit better. And so RIAFs are really these static images. We assume that there's just, the image is dominated by this average type of structure. But Sagittarius A star is highly dynamic, and it actually flares around once a day. And one of these explanations for what these flares are is actually you have a magnetic reconnection event in the accretion disk, And this injects some non-thermal hotspot that orbits around the black hole. And this is what the gravity collaboration saw in 2018. So namely, during an infrared flare, they saw the center of light of Sagittarius A star do orbital motion. And this was actually predicted all the way back in 2006 by Avery Broderick and Avi Loeb. And so what this suggests is that during a flare, you have these hotspots that traverse around the black hole. And one of the questions is can the EHT measure this? And so to test this, we considered one of these hotspot simulations. We ran it over a couple of orbital periods, and then we tried to model it with the EHT 2017 telescope. And one of the downsides of this is that when you try to model this, every time you try to explore your space, you have to do a whole bunch of ray tracing, basically reconstruct an entire image. The upside, though, is that while you have an incredibly high computational expense, is that you can get a very precise measurement of spin. And so what we found was that the EHT 2017 array, if it observes one of these hotspots, is that it can actually recover spin, and the spin measurement is something like sub%. And so this is really exciting because it suggests in the next few years, the EHT array may be able to get a handle on spin. And what's more than that is that if we actually catch multiple hotspots, and we probably will in the next decade or so, is that we can get multiple independent measurements of space-time around the characteristic hotspot radius. And so using that, you can kind of get a tomographic map of space-time, so you can measure how spin changes as you get closer and farther from the black hole, with of course, general relativity's prediction that the spin is constant. And so one of the questions is, why is this working so well? And the reason actually is that it's because we're modeling so close to the horizon. And specifically, we're leveraging a thing that was given a very thorough explanation by George Wong Byerk in a recent paper, and it's called black hole glimmer. And what it is that because we're modeling so close to the horizon, we're getting a direct physical process, we're getting a direct constraint on the flare formation and then the properties of strong lensing. So for instance, if you have a flare form, it will form here, and then as it starts to travel around the black hole, it will start to shear, and it will look like this. But what's happening is that there's a time delay from this primary image. This primary image, the photons from it will go around the black hole once, and you'll get this secondary image here that appears at some smaller time later. If you wait a little bit longer, you'll have your primary image, your primary hotspot has now gone all the way around the black hole and is sheared out. You have a delayed secondary image, but now you also have this tertiary image here from this original motion. And this is really what we're capturing with this hotspot simulation, is we're capturing all these different time delays from the photons traveling around the black hole. And this is the so-called glimmer that is explained in this paper. And it actually provides a unique measurement of spin, inclination, and the mass of the black hole. And so in conclusion, there's various different ways the EHT can recover information about the space-time. In the first part of the talk, I showed how we can use imaging and the VIDA feature extraction tool to recover information about like the black hole diameter and the image asymmetry. But the better way to do this in the way of the future is to really model directly around the accretion, or model directly around the horizon instead. And this is related to actually also work that Daniel has been working on. And in the future, what you can imagine is combining like imaging, but instead of imaging on the sky, you can image around the accretion flow itself. So what you can do is directly break your accretion flow, your emission region around the black hole into little points or different moving blobs, and then fit that directly. And I think that's what I've.
Awesome, thank you. Let's thank Paul. And okay, I see Avi has a question. Avi, you're muted.
I did. Thank you, Paul, for a beautiful talk. the question I have is why are we confident that, for example, the image we have of M87 is representing the silhouette of the black hole rather than some, dark region at the base of the jet that has nothing to do with GR, that has to do with emission physics at the base of the jet? Do we have evidence that it's not the case?
This is a good question, and I think it comes down to a little bit of a debate that's going on in the community right now. And I would say,
I'm completely I don't know what debate is going on in the community. I'm just asking a scientific question. So,
I would say that's a fair point. You don't know if you're necessarily seeing the funnel wall. I would say there is some work that's going to come out soon that will try to disentangle that. And I would say, though, that the calibration technique we used in the calibration technique we used to go from the ring diameter to the mass of the black hole should include those. So a lot of those GRMHD simulations do have images that are filled with the funnel wall. So that calibration uncertainty should come into there. So the mass of the black hole doesn't matter too much. Now, interpretation of whether we're seeing a lensed ring is a little bit harder, and I think I would say stay tuned.
That was not my question. My question was not whether it's a lensed ring, or my question was, are we seeing a dark spot at the base of the jet that has nothing to do with GR versus the black hole region? How do we know that it's the black hole region?
I would say stay tuned. There's going to be a paper coming out pretty soon that I think will try to explain some of this.
Okay, but are you saying that there is a good answer to this question?
I would say there's a reasonable answer to this, or there is a potential answer to this.
And so from your perspective, this paper that is about to come, from your perspective as a scientist that looks at it completely independently of the collaboration.
Well, I can't be independent. I'm on the paper.
Okay, but as a scientist, forget about the group thinking. As a scientist, you yourself think that there is credible evidence that supports the interpretation of a black hole at the center of the dark region?
Yeah, yes,
okay.
I would say so.
Okay, any other questions? Okay, let's thank Paul again, and we will resume after a quick break at 3 p.m.
Hey, Max. I can't hear you.
I forgot to unmute myself. How are you doing?
Good. How are you?
Excellent. Thank you.
Nice talk yesterday.
Thank you. I'm looking forward to yours also.
Thanks.
So it's 3 o'clock. Maybe I should wait another couple minutes, but
Yeah, no problem. I'm not in a hurry.
are you going to tell us in your talk what anabasis means?
No. Well, Achilles was supposed to do that. I think he said, no?
No, you're supposed to find out by yourself, Max. It's research.
You guys are just showing
Yeah.
off your big vocabulary.
That's true.
Okay, let's go ahead and get started.
Okay.
So we're very happy to have Shahar leading off this last session. He is a physicist. He joined us at Harvard in 2018, and he'll be telling us today about photon ring autocorrelations.
Okay, so thanks very much for the opportunity to speak in this great conference. It's been really interesting. I will tell you about this work which appeared 2 months ago in collaboration with Michael Johnson, Alex Lupsasca, and George Wong. So we saw the first image of a black hole last year, which is a great achievement. But of course, a spoiled theorist like myself can say, oh, but this the resolution is still not great, so what can we learn more? And indeed, we know that if we had an infinite resolution, we had a telescope that we could zoom in into the real black hole, then we would see lots of fine structure there, which is kind of hidden and blurred inside the current image that we have. And it will be very interesting, and also the purpose of this talk today, to kind of discuss what kind of structure is there hiding inside this image, and how can we see it. So what does a black hole look like? This turns out to be not such a simple question to answer. It was pioneered already in the 70s by Bardeen, Luminet, and others, and maybe even before by Bardeen, as Avi said yesterday. And this is really answering this question. One rests on 2 pillars. One is the complex astrophysical phenomena happening in the vicinity of the black hole, which generates the light for the image. And the other is general relativity and the Kerr geometry that lenses this light. So it's 2 different pillars. The general relativity pillar is also more universal in the sense that it depends on fewer parameters, only on the mass and spin, maybe inclination of the black hole. And the accretion flow usually has more parameters than that. To exemplify this, you can see these images down here, which generated by the EHT collaboration. And you can see various different scenarios with different astrophysical parameters. You can see that some features in the images are universal and some are not. We will be interested today in a universal feature, which is the photon ring, a bright ring of enhanced intensity on the image. It has only about 10% of the total flux, but it stands out. And as you can see, it appears at the same place in all these images. So there is universality about it. How do we generate an image of a black hole? Let's imagine that we know the dynamics of the accretion flow, and we only need to say what's the image. So that's done basically by geometric optics and a curved geometry. we need to take a screen for an observer far away from the black hole and shoot back null geodesics from that screen into the geometry and pick up the photons as this null geodesic intersects emitting matter near the black hole. This is done in practice by the radiative transfer equations. We need to integrate the contributions to the intensity on this point on the screen along the path of the geodesic. So sigma is the affine parameter along the geodesic. Curly I is the specific intensity at the point on the screen. And curly J is the emissivity in the bulk. And we're assuming no absorption for simplicity, so optically thin emission. A point on the screen labels our geodesic and tells us what the impact parameters of this geodesic are. So we pick a point on the screen, we shoot back a geodesic, this determines the geodesic, and this radiative transfer equation tells us what's the intensity on that point. So in order to understand black hole images, we need to understand geodesic motion in Kerr. And luckily for me, this was reviewed very nicely yesterday by Mina and Delilah. So I really will gloss over this pretty quickly. So we have geodesic motion in Kerr is integrable. We have 4 conserved quantities. The most non-trivial one is Carter's constant, which is a combination of the polar momentum and polar angle. For light rays, actually we have only 2 non-trivial conserved quantities, lambda and eta, which are the rescaled azimuthal angular momentum and rescaled Carter constant. And due to the existence of these conserved quantities, we can reduce the geodesic equation to first order form and solve it by quadratures. In this form, and the radial equation, for example, is can be thought of as an effective problem of motion in 1 dimension with some potential big R, which depends on the radius, and these 2 conserved quantities, lambda and eta. And specifically here, we will be interested in the critical orbits, which happen at the maximum of this radial potential, which allows the geodesic to sit at 1 fixed orbit, but it's an unstable point. So these critical photon orbits are determined by this condition that the radial potential and its first derivative vanish. The second derivative, of course, tells us that it is an unstable point. Okay, and if we invert these equations, we can solve for lambda and eta of this critical orbit happening at some orbit that at some radius that we call R tilde as such. Okay, so these critical orbits in Kerr are a 1-parameter family labeled by their critical Boyer-Olympus radius R tilde, which for Schwarzschild, you have only 1 radius like that. It's the photon sphere happening at R equals 3m. But for Kerr, it can range for maximal spin between m and 4m. So between the horizon and Boyer-Olympus coordinates up to 4m. This 1-parameter family of critical orbits traces a closed curve on the screen of the observer, which, as we said, can be thought of as parameterized by lambda and eta, the impact parameters. So this, so these are the critical orbits labeled by R tilde. And this is, as Delilah described to us really nicely yesterday. This critical curve also tells us where a brightness enhancement will appear generically when there's optically thin emission. It will appear very close, exponentially close to this critical curve. And in Kerr, there's this interesting feature that the brightness enhancement, which is formally a logarithmically divergent brightness enhancement, comes with a coefficient in front of it, which is 1 over gamma, where gamma is the Lyapunov exponent of the orbit, roughly the rate of instability of the orbit. So if we're talking about an orbit which is very unstable, with a high curvature of the potential at the point of the critical orbit, then this brightness enhancement will be smaller. And if the orbit is actually close to being stable or marginally stable, then this brightness enhancement will be larger. To get some intuition into these photon orbits, we can look at this great demo made by Leo Stein. And this kind of will just help us get a feeling for what these critical orbits are. So I can play here with the spin and with R tilde, the critical orbit radius. Let me crank up the spin to maximum because it exemplifies everything more nicely. The outermost critical photon orbit is 4m, as I showed you. And then I can look at smaller radii. You can see that these geodesics have a non-trivial structure. They oscillate in the polar direction, they extend in the azimuthal and of course time directions, but they stay at a fixed Boyer-Lindquist radius. There's one special photon orbit which actually closes to a sphere. This is the orbit that has vanishing azimuthal angular momentum. And then I can go to smaller radii, which are co-rotating photon orbits, until I reach the innermost one, which is the co-rotating equatorial circular orbit, which appears very close to the horizon in Boyer-Lindquist coordinates. Okay, so that's the family of photon orbits, and we understood lots of things about this in this paper last year, and also suggested a way to measure this in experiment, as Mina described yesterday. So this is this animation that shows us how the photon ring is composed of different subrings. So most of the images, the n equals 0 direct image, which doesn't undergo any extra half orbits around the black hole. But then we have the n equals 1 subring, which does undergo 1/2 orbits around the black hole and appears much closer to the critical curve. And then we have the n equals 2 ring, which appears exponentially closer to the critical curve. It's much fainter in flux, it's exponentially fainter, but it's also very sharp. And the totality of the image is the sum over all these subrings. Okay, and also Mina discussed yesterday that this could be measured, and just by going to longer baseline in order to resolve really these fine distances in the image. And then if one actually manages to measure this demagnification factor between two subrings, this will tell us what the gamma, the Lyapunov exponent, is corresponding to that specific angle on the critical curve. So at every angle we have a different Lyapunov exponent. In principle, we can measure this quantity. It's a function of R tilde. For every angle we have a Lyapunov exponent, which tells us how these how these two widths are related to each other. This width, the ratio is exactly the Lyapunov exponent. Great. So that was the time averaged image, and importantly, it's not just intensity; it's the time averaged intensity. And the question is now, what next? So one thing that we can do is, of course, refine this suggestion and suggest, for example, Tesla's GR based on the precision measurement of the time averaged intensity. And this will be discussed in Alex's talk. I will tell you today about a suggestion for new observables to look in, which are not just the time averaged intensities, but something else. So why do you think there will be something else in the EHT data? Well, it's kind of amazing actually how much data the EHT takes. It takes petabytes of data, so much that can't be sent even over the internet. One needs to, so the EHT actually shipped the data physically on hard drives in order to correlate them at a central place. And so there's really a lot of data here, and only a few kilobytes are used for the image itself. So there's kind of information loss here. So maybe it's a new information paradox, or how can we extract more information from this data? That's the question. So another hint is that we know that there should be time dependence in the image. So Maciek and others also talked about this point. we know that there should be significant time dependence. And this is also related to maybe looking at higher point correlation functions. Why am I talking about higher point correlation functions? Because, well, the EHT already looks at correlation functions, but correlation functions of the electric fields in all different pairs of telescopes. This is basically the quantity which is directly measured by the Event Horizon Telescope, the electric field as a function of time at each telescope. And then you take this function of time, two functions of time, two different telescopes, you correlate them at a specific time delay. And this gives you a single visibility or a Fourier component of the 2D image, corresponding to, so which Fourier component it is, that's determined by the spatial separation vector and frequency of the measurement. Okay, as you can see here. So this is one thing that EHT already looks at, but you can ask, okay, maybe look at more general correlation functions. Why not do that? We have already E of t for each eye, for each telescope. So this is indeed related to what we will propose today, this new observable, which is the 2-point correlation function of intensity fluctuations, where the intensity fluctuation is defined as the intensity subtracting the time average piece. Okay, and it's related to this story because this is, roughly speaking, a 4-point function of electric fields. Okay, so each eye is a 2-point function, so this is like a 4-point function. But I don't want to get in too much in detail because of this. Just think of it as the 2-point correlation function of intensity fluctuations. So just to exemplify what our suggestion is, we want to study this 2-point correlation function, which is the intensity fluctuation at some time and angle on the photon ring, and the intensity fluctuation at some other time at some other angle. And then what we want to compute is this curly C, which is the correlation function delta I of t phi, delta I of t prime phi prime. Okay, so and you can see this is a numerical simulation. You can see that you expect to have fluctuations on the photon ring. And moreover, these fluctuations must be correlated somehow. Why do we think they must be correlated somehow? Because imagine, okay, this is already kind of close to the model that we will study here. Imagine that we have some thin disk around the black hole, and we have some flare happening in the disk, or some event. The emissivity along the disk is changing in time. So imagine that we have some flare here. This flare is connected to the screen of the observer here on the right-hand side through formally an infinite number of null geodesics, but practically some number of null geodesics, different null geodesics, and therefore you will see flashes appearing on the observer screen at different points at different times. But all of these flashes practically, except for the n equals 0 one, will appear very close to the photon ring. So we do expect on the photon ring to have significant correlations between different angles and different times. So what is the quantity that we will study precisely? It will be this correlator. So we can start with a 3D correlator. That's the most general thing. We count the dimension as 2 screen dimensions and 1 time dimension. Okay. And this 3D correlator depends on really TT prime, phi, phi prime, rho, and rho prime, the coordinates of the 2 points. And this is how it's defined. Now, as I just argued, it makes sense to integrate out the radial direction using these 2 integrals. So the direction perpendicular to the critical curve, this direction I want to integrate out using these integrals, and just think of the whole thing as one unresolved ring. And also, if we want, we can integrate out the angles as well, just by performing these phi integrals here, and obtain so-called light curve correlation, which depends only on the separation between the 2 points. Now, I want to comment one more thing, that this 2-point correlation function we incur it will depend only on the time separation between the 2 points, we suspect, because we think that the source is variable, but the statistics of the source are time independent. So it will depend only on the time separation between the 2 points. But for general inclination of the observer, it will depend separately on the 2 angles, because the observer actually breaks the axis symmetry of the space-time. But as we will analyze the special case of a polar observer, an observer that actually sits on the pole, then the correlation function will depend only on the difference between these angles. Okay, now in order to compute this thing, I will need to introduce a little bit more concepts related to near critical null geodesics in Kerr. So we already discussed the Lyapunov exponent gamma, but there are 2 more important quantities, tau and delta, which I will describe now. So gamma tells us what is the ratio between the separation from the critical radius when your geodesic undergoes many half orbits around the black hole. So how close you are to the critical radius. This is gamma. This is what we discussed. And there's also tau and delta, which tell us what the time period and azimuthal period, as you can see in the figure here, of this orbit are. Okay. So this is these 3 functions, basically functions of our tilde, will really tell us everything about the lensing of near critical null geodesics. So to understand this point, to get some intuition to this point, let's see how these 3 critical exponents affect lensing when we're looking at the black hole from the pole face on. Okay, so imagine that you have some Kerr black hole with the spin axis either directed towards us or away from us. And this is the critical curve of this Kerr black hole that we, of course, don't see directly. And then we have some event here, like a flare or something else. This is exemplified by this image over here. So it will have an n equals 0 image, an image that doesn't undergo any extra half orbits around the black hole. And then it will have an n equals 1 image, n equals 2 image, n equals 3, etc., etc. Now, in the universal regime, which n equals 2 and 3 are pretty much into the universal regime, so the location and time where this event appears on the screen are very simply related by this triplet of critical exponents. And here we're talking only about really numbers, gamma, delta, and tau, which correspond to the critical orbit happening, which happens with lambda equals 0. So it's the critical orbit that has 0 azimuthal angular momentum and thus is able to reach the pole. So these n equals 2 and n equals 3 images are related by a shift in angle by delta 0, a shift in time by tau 0, and they appear, the n equals 3 image appears closer to the critical curve than the n equals 2 by a factor of e to the minus gamma 0. So this is the very simple way in this polar case in which the higher order images are related to each other. So that's for every space-time event or for every flash on the screen. Now, the goal will be to understand what this implies for the correlation function of random emission near the black hole. So this is our model, our very dumb, simplest possible model for random emission in the vicinity of the black hole. So we assume a geometrically thin disk as well. So it's a delta function in the polar direction. And we assume something very simple about the 2-point function of the emissivity in this disk, delta J. We assume that this 2-point function of emissivity is just some constant times Gaussian falloff in the time direction, radial direction, and phi direction. Okay, this sine squared here just means that this is a Gaussian distribution which has periodic boundary conditions around the circle called the von Mises distribution. And so the 3 other parameters, except for this total fluctuation magnitude, these 3 other parameters are LT, LR, and L phi, which are the correlation lengths in the 3 different directions. Now, to understand what these correlation lengths might be in a realistic situation, we took the most closest to realistic thing that we have, which is a full GRMHD simulation, and checked what these correlation lengths are under this assumption of separability and this Gaussian fall-off. Of course, this is not very realistic, but we are hoping that this gives us some good idea about the order of magnitude of the correlation lengths. So we calculated in the simulation this 2-point correlation function of the normalized of the emissivity fluctuations and computed from that the correlation lengths. And this is what we find. We find the correlation length in T is 3m, in phi is 4 degrees, and in R is 0.4 m. This will be important a bit later. And now we can do our calculation, analytic calculation of this correlation function. And the simplest case would be the polar observer. So this is the case I will focus on now. We need to solve, to find the intensity, we need to solve the radiated transfer equation. But in the case of a thin disk, a geometrically thin disk, the radiated transfer equation just becomes a sum instead of an integral over all the crossings of the equatorial disk. Okay, so we just need to know the fluctuation of the emissivity at each point of crossing, enumerated by I. So we take this, we plug this into the correlation function, our definition, and just compute it. We need to compute these integrals and one of the sums, and use our assumption on this 2-point correlation. And what we get after a few gains with integrals and sums is this result, which is a sum over peaks in T phi plane. Big T and big phi are the separation between times and separation between angles on the ring. So it's a train of peaks. They're separated by integer multiples of tau 0 and delta 0, the critical exponents. And the higher order peaks are suppressed by a factor of e to the minus gamma 0, the Lyapunov exponent. And the width of these peaks is determined by LT and L phi. So graphically, this looks like this. This is a result for the correlation function. We have a big peak in the middle, and that happens for any astrophysical source. But the special features are these additional peaks that appear at this finite separation, and at least with these parameters, with these values for L phi and LT, they're separated. They're significantly separated from the peak in the origin. And as you can see, the separation between peaks is tau 0. In the big T direction, it's delta 0 in the big phi direction. And the relative suppression is e to the minus gamma 0. Okay, so this is really the universal structure, which is determined only by this triplet of critical exponents, correspondingly by the mass and spin of a black hole. So that's the universal part. The non-universal part is really the shape of each of these peaks separately. And that, as you can see, is determined by the correlation lengths. And in principle, it could be also a more complicated structure. If we wouldn't have assumed this really dumb model, we would have gotten something more complicated. Maybe it depends on the velocity of the flow, etc. I mean, there are also many interesting things you can learn from just looking at the shape of each peak separately on the accretion flow, specifically on the statistics of the accretion flow. Good, so we generalize this expression for any inclination analytically. It's a more involved expression. It still demands a bit more study to understand the heuristics at arbitrary inclination and arbitrary spin. And we also use this generalization to study to leading order and inclination, the expression, and that's a bit simpler. And specifically, we can show that this expression that I showed you for the polar case actually persists also for small inclinations. It's also only corrected at order inclination squared. So for example, 17 degrees would be already a good approximation. That thing that I showed you. So the observational prospects, so I think it's really interesting observationally. What would it mean to see another peak except of this middle big peak if we can see another well-separated peak at a different place? And this is kind of equivalent, I would say, to seeing the photon ring, to seeing photons that actually underwent extra half orbits around the black hole. Why is that? Because I don't know of any other source which facilitates this, except of very fine-tuned situations of gravitational lensing, which we have no reason to expect occur specifically there at the black holes we are observing. So seeing a well-separated peak is already very good evidence for a photon ring. This will allow us to test strong field GR, because this is really prediction of strong field GR. These Lyapunov exponents, they're determined directly from the Kerr geometry. It's not some weak field thing. And it will allow us to measure the mass, and interestingly, will also presumably allow us to measure the spin, because this delta zero, the critical exponent related to the azimuthal shift, is strongly dependent on spin. And the really big advantage here is that we do not need to resolve the width of the ring. The thing that really allows us to improve the signal to noise ratio here is just waiting long enough and collecting a lot of data. So we believe that this will allow a measurement even before a space mission. This will allow us a measurement, not to see the photon ring directly, but to measure the photon ring using these correlations, even from Earth. Great, so let me conclude. I showed you this new observable that we proposed for the Event Horizon Telescope, the 2-point function of intensity fluctuation on the photon ring. So a lot of extensions need to be done. We need to understand better the heuristics of our expressions at different inclinations, high and low spins. It would be great to do numerics, in particular slow light simulations in GRMHD, which actually take into account a more realistic scenario. Consider geometrically different disks like puffy and inclined disks, and also try to express our correlation function directly with the raw data of EHD, which may actually help us measure it in a better way, before that we don't need to form an image every time and then compute the correlation, but somehow do it directly from the EHD data. That would be helpful. And also generalizations are in place, like studying correlations of polarization, studying more general correlators of electric fields. What is the maximal information that we can extract from EHD data? And lastly, I think the most interesting thing would be to measure this quantity. So I really hope that will happen. Thank you.
Okay, thanks a lot, Shahar. Let's thank Shahar. Okay, Avi?
Yeah, Shahar, very nice talk. My question has to do with something I was waiting for you to say, but you didn't mention it. And so there is one thing that you can measure with your correlation function, and that is if there is a hotspot, it has an orbital time. And if it survives for a substantial fraction of one orbit or more, you could measure the orbital time. And if you measure the orbital time, you get a direct handle on the spin. You don't need to go into any more fancy stuff, just the orbital time. And if you know the orbital radius of this hotspot, that would solve the problem.
Right. Okay. Right. So I think this is related. So I'm thinking about the situation in which I have random fluctuations, and I can have many different hotspots. And I think the different and I can have different hotspots, for example, at different radii with different periods. And I think the effect of these different periods will be roughly to change the shape of this peak, say, for example, something like this, which is elongated in one direction, which is determined by the velocity of the flow, something like that. It will not change the universal structure in the sense that all the other peaks will also, look something like this, etc. So I can know something about the details of the flow, which is also, of course, very interesting data, by looking at the shape of each peak. Yeah, so
there is more information, yeah.
Yes.
Just to follow up on Avi's point, so we would expect if we had no spatial resolution whatsoever, and we could measure the periodicity, that the shortest periodicity would be the orbital period of the ISCO. And that depends very sensitively, I'm just saying what Avi was saying, that depends very sensitively on the spin. So it seems that if you could had the technology to measure this, it would be much easier to, there would be something more direct that would give you a lot of information before that. Is that?
That's the shortest periodicity
am I
for
missing
orbits, I
something?
would guess. But then you have also the period of this 15 or 16 m of the tau. Right? So.
But that's a longer period, right? So you just Fourier transform in time the signal coming with no spatial resolution. And you wouldn't expect to see many, it'd be very surprising if you saw any substantial signals with a period shorter than the period of the ISCO. And so if you just had a good Fourier transform, time Fourier transform of the luminosity, that would be all it would take, I think, to get a pretty sensitive measurement of the spin. And that's,
thank you, Andy. That's
surely
that was
something
exactly
which is
right. So you're suggesting maybe to,
but I don't know why. I've asked the people, I don't know why nobody is trying to do this. There must be a reason.
Well, that's exactly my point, Andy.
But
Thank
surely,
you for asking.
right. So like if I'm looking now at this 1D correlation function, only of the light curve correlation function, so this will also have a peak in the origin. And then what you're saying here is that we will have some other peak here. And then if we can actually separate them. Is that true?
Yeah. Yeah.
Something
Sure.
like that. Yeah. I mean, I think, yeah, it makes sense. I mean, I
That's
think
what we do with atoms.
the only question is whether we can say there's a really two well separated peaks, or do they just merge and we can't separate them? I don't know.
Now, how would you get anything with a time scale? How would you ever, what reasonable physical mechanism would ever give you a signal from M87 with a period of 1/10 of the period of a particle on the ISCO? You'd never expect to see that.
All these points, right?
It couldn't be associated with CR.
Yeah, it's just like local correlation in the accretion flow. The fact that if I have a bright hotspot, it stays bright for a while. It's only that.
If it's staying bright for a while, that's not a period. It's not oscillating.
Right. It's not oscillating, but still it's the thing responsible for the fact that this is not a.
Oh, you have incredibly shorter wavelengths associated with fluctuations of the plasma or something, but no, there should be a huge peak at the period of the ISCO if we could do a Fourier transform.
Yeah, that's also
there's all kinds of swirling massive stuff. What?
That's also the brightest
thing that.
Yeah. It's also the region where most of the emission takes place, and indeed the radiative efficiency is the highest near the ISCO. So, yeah, exactly.
Yeah. So you should see longer periods associated with things outside the ISCO.
Right. Yeah, I agree. I think like from an observational
how come nobody talks about this?
From an observer point of view, I think the question is only whether these two peaks are well separated or not, how wide they are.
Well, surely if there's a problem with separating peaks when you have no spatial resolution whatsoever, there will be a problem when you start fine graining it.
Have you tried?
Why would there? What physics would give you? What physics would give you a significant signal at a period of half the period of the ISCO?
if I can, I think there are many experts on this call who can speak to this better than I can, but the GRMHD models that are favored in the EHT data bank feature emission going and increasing all the way to the horizon. So if you look at older papers up to 2012, there was a lot of discussion of ISCO periods and hotspots at the ISCO, but that seems to have been replaced in favor of models that have emission going all the way to the horizon.
How is that possible?
We're talking about time, not R.
I mean, the plunging stuff is not periodic.
You're saying there's also, yeah.
If you look at,
we're not talking about R, we're talking about period. The plunging stuff?
There is a claim. My understanding is that there's a claim that the emission in the GRMHD simulations is not dominated by ISCO emission. Is that fair?
Isn't what I was talking about. We're talking about the periodicity, not the whole luminosity.
And the shortest period is
with a Fourier transform.
Yeah,
it doesn't. The emission doesn't have to be done. When you Fourier transform it, you pull out that piece.
Well, there should also be periodicity on the scale of the photon orbits, and those.
That's
up until
that's
very
longer.
Spin, those are shorter periods than the ISCO period.
What?
Yeah, it's only at very high spin that the ISCO enters into the photon shell.
Okay, whatever the shortest period is. Okay, if there's some if the spin is lower and the ISCO is outside and the photon orbit is inside the ISCO, then fine. Then the shortest period is the photon orbit. Then we should look for that period.
Yeah. So
for high spin, what I was saying was true for relatively high spin.
Yeah.
What?
Yeah. So
but there's going to be a shortest period. This 1D thing. Right. If the ISCO period is longer than the photon orbit period, then we look for the photon orbit period.
Yeah.
But there is this thing isn't emitting at all frequencies. There's a lowest.
Anyway, there is a paper to be written on this.
Great.
Okay, Maciek?
So I didn't take part in this discussion. I had a different question, but let me just make a comment. Just one of the things that are going on that make this complicated is that there are other forces at play. There could be dynamically important magnetic fields, there could be pressure, and of course you can have circular orbits all the way to marginally bound orbit with the presence of external forces. So it's all not that clean, but that is not my question. That is something interesting to discuss separately and probably for much more extensive period of time. But Shahar, that was really very nice. When you were giving this talk, I started wondering, because I'm also a little bit involved in this sort of studies. I wonder now if you could actually produce these sort of signatures without anything like black hole. What I mean is, what if you had a periodic source, but every next peak in this period was getting decoherent with respect to the previous peak? I don't know. I'm just trying. Do you think there is a way to make it up? Because you say it's really a signature of a black hole, signature of having these photon orbits. But I'm wondering if I could reproduce it without any of that, just by having a periodic source that correlation between next beep, next peak is decreasing with this Lyapunov exponent. Could I engineer a source pretending to be a black hole?
Well, I mean, I think that if you engineer, I mean, you can do anything, but I don't think that you can. I can think of any astrophysical source that
I don't know, some kind of a quasi-periodic oscillating stuff that getting.
I don't know too much about that. I mean, also there are people that speculate that maybe that's related to black holes too, right?
Yeah. Okay, thanks.
Yeah, I don't know. I don't know of any. I mean, this you would need to fine tune your thing, I think, to behave like
Because
that.
it looks to me that if I wanted to engineer such signal, I would, but then that would be, then seeing such signal would also be showing that somebody is engineering it, and that's even more fascinating than seeing echoes of black holes.
Okay, thank you very much. It looks like we should move on to our last talk. So thank you, Shahar, for the excellent talk. So our last speaker is Alex Lupsasca.
All right. Can you see my screen sharing?
Yeah. Okay.
Great.
So we're very happy to have Alex Lupsasca. He just escaped his near critical orbit about Harvard and moved to Princeton. So we miss him, but we're glad to have him back at to round out the Black Hole Initiative conference.
Thanks a lot for inviting me again to speak. I'm very excited to tell you about, again, the black hole photon ring, which you've heard about a lot today. So I'll give a brief review of the structure of this ring, and you've heard a lot about this already in some earlier talks in this conference. And then I'll try to focus on an experimental proposal for a test of GR via measurements of the shape of the black hole photon ring, which is recent work with Sam Gralla and Dan Maroney at the University of Arizona. So last year, in April of 2019, the Event Horizon Telescope collaboration released the very first image of a real black hole in the sky, which is a real historic achievement and an amazing technical feat. The black hole at the center of the galaxy M87 star, is located 50 million light years away. And now we have a high resolution, well, a close-up picture of this black hole. And of course, we're all impatient to see an even clearer image. And we think that this thick donut of light, which encircles a dark patch that we think is the black hole, should actually resolve eventually to a razor-thin photon ring, this ring of light that we see on this GRMHD simulated image. And initially, this expectation that there's a ring, a very narrow ring embedded in an image of a black hole, was based on looking at the data bank of GRMHD simulated images that the Event Horizon team produced, and noticing that they all have this characteristic ring shape. So over the next few years, as the Event Horizon Telescope improves its detection capabilities, we'll be able to learn a lot about the astrophysics of the source and learn about the accretion flow and the astrophysics and the kinds of things that Angelo Riccardi and Paul Tiede have already talked about. But I want to focus particularly on this universal feature, which dominates the image, this photon ring, which is there always because of gravity and the Kerr geometry of the black hole. So I think by focusing on this photon ring, we can really probe strong field GR. So in this talk, I'm going to address three questions. What is the origin of this ring of light? How can we better resolve it? And what can we learn from it? And just to give the punchline from the beginning, this photon ring is a universal, that is to say, a matter-independent effect that follows purely from general relativity, and has a very rich and intricate subring structure, which we've come to understand over the past year, which is entirely governed by three critical parameters, gamma, delta, tau, which we've heard about in Shahar's talk. To better resolve it, well, it's obviously present in images, such as the simulations that I just showed, but it's also present in the Fourier transform of images, which is what we measure experimentally with very long baseline interferometry. And this ring actually contains many subrings, which produce universal signatures on long interferometric baselines that we may be able to detect with space-based interferometry if we target M87. And that's exciting because there's a specific observable that I want to advertise in this talk, which is the shape of the photon ring. It happens to be remarkably insensitive to the astronomical source profile and could be used to provide a stringent test of strong field GR using space-based interferometry. So those are the main points, and now I'm going to walk through all of them in order. Let me say, though, that this is an active and growing area of research. I tried to compile a list of recent papers on the photon ring, and this is not an exhaustive list. There's been a rapid succession of exciting theoretical developments that have been spurred by the release of the image. We've heard from Mina Himwich yesterday about the polarization inside the photon ring. Shahar just talked about autocorrelations in the photon ring and how we may even image them sooner from Earth. And as Yao mentioned this morning, this has even penetrated mathematics, and there are now studies of the mathematics of the photon shell. So I think there's a growing number of papers, and there are many more left to write. I'm going to try to focus on 2 or 3 papers that have guided my thinking in the past year, starting with this paper, which was my introduction to the subject. It's a work that was conducted at the Black Hole Initiative together with theoretical physicists, astronomers, observers, instrumentalists, and which was a great deal of fun and only made possible because of the Black Hole Initiative. And in this work, we started to understand the subring structure and these Lyapunov exponents gamma. And I later figure out some more details of this stuff with Sam Gralla, and I'm just going to give you a lightning review of what we've learned. So everybody knows that a black hole has an event horizon, but just outside of it, there's this photon shell, which is a region of spacetime in which, from which light can still escape, but nonetheless, gravity is so strong that it can deflect light rays around the black hole and possibly make them execute multiple turns around the black hole. So we're going to call these bound photon orbits critical orbits. And they're characterized by 3 critical parameters. So the 2 simplest ones to describe are delta and tau. So for each radius in the photon shell, you can have one of these bound orbits, which zooms about the black hole, and you can see them in 3D on Leo Stein's website, and Shahar just flashed that in the last talk. So for each bound orbit at a given radius, you can define delta and tau to be the azimuthal angle swept per half orbit, where a full orbit is bouncing in theta from the bottom to the top of the shell and back. So a half orbit is just going from bottom to top or top to bottom. So in 1/2 orbit, as you go around like this, you sweep out some angle delta and you incur a time lapse tau. So these 2 are fairly easy to describe. And lastly, there's a 3rd exponent, which is very important in the story, and it characterizes the instability of nearly bound orbits. So we can think of it as a Lyapunov exponent because it describes the exponential rate of geodesic deviation in the radius of light rays if they're not exactly tuned to be bound. So of course, if you have a bound orbit, in principle, it stays there forever, but these are unstably bound orbits. So if you push them off a little bit, their radius will exponentially grow. And this exponent gamma, which controls the rate of exponential deviation per half orbit, is an important critical exponent. Okay, so these are the 3 main parameters that characterize these orbits locally, and they will also turn out to control the properties of images that we see from this region far away. So to understand this, I need to briefly describe a salient feature of images of black holes. So Bardeen in '73 taught us how to describe the observer screen of somebody looking at a black hole with Cartesian coordinates alpha and beta. And it turns out that there's a very important curve on the screen, which has come to be known as the critical curve, which Bardeen derived, and consists of, it is the image of critical light rays in the observer sky. So what do I mean by this? Well, if you aim light rays, so if you imagine shooting a light ray back from your observer into the geometry, if you aim it inside this curve, eventually it will fall into the black hole and pass through the horizon. On the other hand, if you aim a light ray outside here, it will come close to the black hole, but eventually get deflected back out to infinity. And if you aim exactly on this critical curve, you have to be infinitely precise, then actually the light ray will descend and eventually asymptote to a bound orbit in the photon shell where it will in principle unstably orbit the black hole forever. So a very funny feature of this critical curve is that as you go around it, you're not actually looking at different angles around the black hole, you're actually varying the radius around the black hole that you're looking at, which is really a warped feature of the geometry brought to life on your screen. And there's a lot more to be said about that, but for the purpose of astrophysics, what we need to discuss here is that, of course, it's very hard to aim a light ray exactly on this unstable locus, the critical curve. But if you aim close to it, you get these so-called near critical light rays, which can execute multiple orbits. And it's this phenomenon that really underlies the photon ring. So what do I mean by this? Well, let me briefly describe how lensing by curved black holes works. The idea is that light rays near the critical curve can circumnavigate the black hole multiple times, and that means that a single light source can connect to an observer along multiple rays. And this was really the fundamental insight behind what Shahar talked about. And let me briefly review what he also described. So let's take the simplest possible case where we're an observer aligned with the spin axis of the black hole, looking down at an exactly equatorial disk. So we'll get a direct image of the disk from the so-called n=0 light that doesn't execute any half orbit around the black hole, but just comes directly at us. And then we'll get an additional image from light rays that are initially shot down, but perform an additional half orbit around the black hole before reaching us again. And then there will be an n=2 image from light rays that circumnavigated the black hole once. And then we can get n=3, n=4, and so forth. And by expanding the geodesic equation, the null geodesic equation in Kerr in this large n parameter, in the large orbit number, we can obtain a very simple description of how these higher and higher n images are lensed. So if you look at your black hole, and in your picture, this black circle is your critical curve. And so in your mth image of the disk, you see this color wheel. Then in the m+1th image, the next image of the disk, you'll get the exact same image of the emission around the black hole, but just lensed in the following manner. First, it will be exponentially squeezed to the critical curve. So the distance of the n+1th image is exponentially smaller than the nth distance by an amount e to the minus gamma. So the Lyapunov exponent that controls the instability of the orbits also controls the demagnification of images. And this factor is smallest for Schwarzschild when it's exactly e to the minus pi, which is about 5%. And as the black hole spin grows, this demagnification factor also grows until it's about maximized for an extremal black hole at almost 10%. And because the black hole spins, it can also drag around these light rays with it. And so as you increase the spin, you find that the color wheel is rotated more and more. So for a Schwarzschild black hole, the light rays always appear on one side or the other of the black hole. So each higher image is rotated by exactly pi, or 180 degrees. But as you spin up the black hole, there's more frame dragging. And so eventually at maximal spin, you can get almost 3/4 of a turn. So that's the parameter delta, which Shahar also discussed. And lastly, there's a time delay tau, which is only weakly dependent on the spin and is always roughly about 69. Okay, so that's the entire picture of lensing by curved black holes. And at least in the high n regime, everything that you need to know follows from these three parameters, gamma, delta, tau. So now let's try to understand what this implies for images of black holes. Well, if you look at an image of a black hole, you want to figure out the intensity at each pixel. So what you do is you ray trace into the geometry, you shoot a light ray back from your observer into the bulk, use the null geodesic equation to evolve your light ray, and then once it enters the source, you use the equations of radiative transfer, which tell you that you're supposed to update the brightness, the number of photons loaded onto the ray, by each time you pass through a small element of emitting matter, loading some photons according to the emissivity of the source, and possibly removing some if they're absorbed. So if you do this, well, I just told you that light rays that do perform n half orbits around the black hole must appear exponentially close to the critical curve. So if you invert this relation, you find that as you approach the critical curve on your screen, the number of half orbits of a light ray that you aim near that curve will blow up logarithmically with this coefficient controlled by the Lyapunov exponent. And what this means is that for optically thin matter distributions, there will be a mild logarithmic divergence in the observed ring intensity because it will scale like the number of half orbits, since a light ray that completes n half orbits through the same emission region can collect about n times more photons along its path than the light ray that just comes directly to you. And so the photon ring technically is defined as the bump in the photon intensity which contains this logarithmic divergence arising due to the near critical orbits. And of course, in the real world, this divergence is eventually cut off by finite optical depth effects, so the photons end up getting absorbed. But the striking feature remains nonetheless visually prominent in many ray-traced images of GRMHD simulations. And here's one which Mina already showed yesterday. So generically, if you look at an image of a black hole, you'll have an image of the stuff around it that you see from light rays that come directly to you. These are the so-called weakly lensed or n equals 0 light rays that show the direct emission. And superposed on top of that, you'll have another image of the entirety of the emission region around the black hole, but from light rays that do an additional half orbit. So these are the n equals 1 guys. And because they have to be aimed in just the right way to execute an additional half orbit, they end up appearing aimed close to the critical curve on your image. And finally, the n equals 2 light rays, which perform a full orbit around the black hole, they circumnavigate it once, will appear even closer to this critical curve on your screen because they had to be aimed exponentially more precisely. And when you put it all together, you get the background n equals 0 image, and superposed on top of that, an additional n equals 1 ring, and then an additional n equals 2 subring. And all of these subrings together add up, superposing to produce this photon ring structure. And so, as I said, this photon ring substructure has been confirmed by numerical simulations. So George Wong last year produced this very high resolution GRMHD simulated image. And if you look at horizontal and vertical cross sections of the intensity profile, which are shown here in blue and red, you'll find, if we zoom in on these patches, that there's the direct emission, which is this stuff from here to here, that's n equals 0, and you can see it here. On top of that, you have this pencil thin n equals 1 ring, which stretches from here to here, and that's shown in blue here. And then you can even see this razor sharp n equals 2 photon ring, which appears here. And then you can't really see on the image, but there's an n equals 3 and so on and so forth. Okay, so now this wraps up the summary of the theory. Let me say everything again in words just to catch you up. General relativity predicts that embedded within an image of a black hole, there lies a thin photon ring, which is itself composed of a sequence of self-similar subrings. Why are they self-similar? Well, because each subring is a lensed image of the main emission. So you're seeing the same thing again and again in relativistic images, which are indexed by the number n of photon half orbits executed around the black hole. And this phenomenon of Kerr lensing is completely characterized by 3 critical exponents, gamma, delta, and tau, which respectively control the demagnification, rotation, and time delay of successive images. And now the last thing I want to draw your attention to in these plots is that the photon rings, these subrings, we can see them here in the simulation, they converge to a critical curve, which is the critical curve that Bardeen derived. But that curve in itself is not observable. It's a theoretical curve that these photon rings converge to, but yet are distinct from. And so importantly, you can notice here that these photon rings don't have exactly the same shape. So now there's a lot of structure that I've described, and it would be great to start to observe some of this in real black holes by looking at the sky. And I think perhaps the low-hanging fruit that would still be ambitious and really interesting is to look at the n equals 2 photon subring and try to measure its precise shape. Now, the reason I'm going to focus on the n equals 2 ring is because n equals 0 is just astrophysics. You're just seeing an image of the source around the black hole, whatever that is. N equals 1 is not so much in the universal large n regime because you're expanding in 1 over n. And so when n equals 1, that's not a very good expansion. But n equals 2, as I'll argue, actually is already getting into the universal regime, which is governed by GR. And of course, in principle, the GR effect gets stronger and stronger as you go to higher n, but unfortunately, you can see that the flux in these subrings gets exponentially small. So n equals 2 is really the sweet spot where you're already in this universal regime governed by GR, and it's still measurable, I'm going to argue. Okay, so this brings me to my experimental proposal, which was made in a recent paper this summer with Sam Gralla and Dan Maroney. And there's also some useful background in these papers, which I'll briefly describe, on how we hope to actually measure this n equals 2 subring. So let me briefly review how the measurement is supposed to be conducted. So we're envisioning using interferometry, and a radio interferometer measures essentially this so-called complex radio visibility, which is a two-point function of the electric field correlated across pairs of satellites, as Shahar just reviewed. And it turns out that this complex visibility, under some mild assumptions, is the Fourier transform of the image. And so we don't directly see the image, we sample its Fourier transform, and in particular, each telescope pair samples a point U in Fourier space, in the Fourier transform of the image, and that point U has coordinates which are given by the projected separation along the plane perpendicular to the line of sight to the source, measured in units of the observation wavelength. And the key insight in the paper with Michael Johnson and all our friends at the BHI from last year is that if you have a very narrow ring, which has some diameter d and then some much narrower width w, then when your baselines are in this interval, so when the length of your baselines are large enough to resolve the diameter of the ring, but not large enough to resolve its width, then you get a very simple, clean signature of the ring. In particular, you find a signal with a period that encodes the ring diameter. So how does that work more precisely? There was a nice paper by Sam Grala this summer that gave a very specific answer. So suppose you have a very bright, narrow curve in your sky, and you're in this regime where your baseline is large enough to resolve its diameter, but not its width. So it looks like a delta function thin curve. Then it's just an exercise in Fourier theory to show that its visibility, so the Fourier transform of the image, the observable that your interferometer can see, takes the simple form. Now this is a complex object, but if you take its absolute value, you get the visibility amplitude. And the point is that in this regime, you get a nice, simple ringing pattern. And the period of this ringing is 1 over the diameter of the curve at that angle in Fourier space. Okay, now in practice, it turns out that the visibility, the complex visibility is fairly difficult to measure. In particular, visibility phase is particularly hard to see because of experimental noise. But the visibility amplitude is significantly simpler to measure. And so it turns out that if you only see the visibility amplitude of such a curve in the sky, like the photon ring, then you can actually only see its projected diameter. And this is an important caveat because, so this is the formula for the visibility amplitude of a narrow curve in your sky. And notice that you're only sensitive to its diameter. And I want to highlight an interesting point here, which is that the projected diameter is actually not enough to reconstruct the exact shape of the curve. So as an example, consider the circle, which is a curve with constant diameter, d. But there are also many other curves of constant projected diameter. And a famous example is the Rayleigh triangle, which no matter what angle you look at it from, always has a projective diameter of d equals 2r. So it would cast the same 2D shadow as a circle, but it has a very different shape. And so if we perform observations of the visibility amplitude of a narrow curve in the sky, we can tell its projected diameter, but we can't tell, we wouldn't be able to tell the difference between a circle and a Rayleigh triangle. And in general, there's a nice calculus. This is a kind of rabbit hole, but you can always decompose a curve into a projective diameter plus another centroid motion. So for the purpose of this talk, all you need to know is that if you have a perfect ellipse, this is the formula for its projective diameter as a function of angle phi, and its semi-minor and semi-major radii R1 and R2. So now I want to turn to the experimental proposal, which is to test GR by measuring the photon ring shape. And there are really two questions to address here, one of principle and one of practice. So the first question is, I've argued that if you look at the n equals 0 signal, you're basically just seeing the astrophysical source. But as you look to higher n images, you're starting to see the lensing pattern, which is governed by GR. And because the rings get narrower and narrower, they start to dominate on long baselines. So in principle, we think that by going to very long baselines, we should be able to abstract away the astrophysics and just focus on the properties of the photon ring and GR. But does this happen in realistic models? So could we even test GR in principle if we had a perfect instrument? And the answer I want to give is yes, because in models of M87 star, the n equals 2 photon ring diameter can always be measured from the interferometric signature. And we find that it's always that of an ellipse, independent of the astrophysics. And again, I want to emphasize this is non-trivial because the ring shapes converge in n to that of the critical curve, but in principle, well, you don't know a priori what they are without computing them. So this result holds to 1 part in a million or 10 million for the range of models that we've looked at, and this is a robust prediction of GR. And then the second question is, can we actually achieve the experimental precision required to carry out an interesting test in practice? And we've proposed that the answer is yes, because we think the basic requirements can be met if you have a large inflatable aperture in space, together with some new detectors that are being developed now, placed in a far Earth orbit, roughly corresponding to an Earth-Moon distance. And we did a simple forecast, and we found an incredibly high precision for a potential test of strong field GR and the Kerr hypothesis. So I'm not going to go into all the details. I'm just going to flash these slides and tell you what we did. So we considered many black hole spins and observer inclinations, spins from 0% to 100%, observer inclinations from 0 degrees to 30 degrees, which we think are basically compatible with M87. And then we considered several source models of emission. We only consider stationary axisymmetric equatorial disks, which is a limitation of this work, but already there's work ongoing by several groups generalizing this to more realistic configurations. And so for various source profiles in the geometry, we ray traced images, obtaining profiles that look just like what was obtained in the high resolution GRMHD simulations. And then we Fourier transformed them. So we computed the visibility amplitude, made sure that it's compatible with the EHT data from the 2017 run, whose data points are plotted here. But then we went to very long baselines. And what we found is that the n equals 0 image dominates here. Then there's the n equals 1 that dominates here. And then we went to the n equals 2 that dominates here. And this here, roughly at 230 gigahertz observations, corresponds to Earth-Moon distances, which are 300 gigalambda. And what we found is that by the time you get there, you get this very clean ringing signal. We fitted it to the universal signature that is expected for a narrow curve. And we found that indeed we could fit the wiggles that we saw to this formula and infer d phi. So in principle, it's possible to measure the photon ring diameter by going to long baselines. And we found that in all these models, we always got an ellipse to incredible precision. And so this is a prediction from GR for M87. And then secondly, we made a forecast of the precision that we'd expect in an actual experimental measurement with a potentially realistic setup. So, you know, there's a bunch of experimental assumptions that need to be made. I'll just point out that this is the kind of data points that we'd expect to be able to see in the near future with realistic technology, but nonetheless, it's still possible to infer the diameter of the n equals 2 photon ring. In fact, it's very robust. And the idea is to measure the diameter at every angle and try to fit this functional form and find the best fit. And if you find a shape of the ring which takes the form of an ellipse, then you can report a successful test of GR and report how precisely you've tested it. And in this forecast, we got 0.04%. And if you just can't find any parameters in this formula to fit the diameter of the ring, then you have to exclude GR or the associated p-value. So this is the big picture for this proposal. We put a satellite in space orbiting the Earth. As the satellite orbits around the Earth in the plane perpendicular to the line of sight to M87, we perform observations which tell us about, which give us a ringing visibility amplitude from which we measure the diameter of the ring at every angle. We possibly have to do this many times to average over variations. And then we check to see if the observed diameter matches the prediction from GR, which corresponds to the projected diameter of an ellipse. Now, the biggest caveat in this entire discussion is that we can only make observations over, say, a couple of hours at a time, and there may be fluctuations over these timescales. So I'm quite certain that if you observe for long enough, this experiment is possible, but the question is, over what period of time do you need to observe to time average away the fluctuations? So suppose that the image profile is not a perfect stationary axisymmetric smooth profile, but instead there's some additional astrophysical noise, say at this level, then the signal long baselines would look like one of these dotted gray curves, which is a little bit messier. But the point is that here we looked at, like, I think 17 realizations of noise and averaged them to get this black curve, which is the average over many noisy observations. And the point is that all we care about is that the nulls and the phase of the black curve and the green curve, which are the true noise, the true signal without astrophysical noise, match. So the point is, at this level of astrophysical noise, we can still measure the periodicity of these nulls and infer the shape of the ring. But we don't know what the true level of noise in the real signal is. So I think that's the #1 area that needs a lot of theoretical work. So there are many comments and caveats. I've mentioned the biggest one, which is that the experimental forecast is currently at the order of magnitude level. We need more detailed modeling to improve these forecasts. And again, the most critical question is, what is the amount of astrophysical noise? I've been talking to a lot of experts about this, and my current understanding is that GRMHD may not actually be the correct theory to describe the noise in the signal, because, for instance, the mean free path of electrons in the black hole plasma exceeds and possibly far exceeds the Schwarzschild radius. So the GRMHD approximation is a priori not well justified. Nonetheless, the Larmor radius, which is the scale at which the electrons circle the magnetic field lines, is very small. And so you might get lucky, and GRMHD could still be a good approximation even in this regime. And this is still very much worth exploring. Unfortunately, there's also a technical limitation, which is that the resolution required to resolve MHD for turbulence in these simulations seems to lie far beyond the present reach of even the best GRMHD codes. So I think it's important to push the GRMHD simulations, but also try to come up with a more systematic approach. And I think there are various efforts underway along these lines. And lastly, this proposed mission is currently single purpose, but obviously if we're going to send a big radio telescope in space, we should also think of other applications, and it would be good to think of synergy. So if anyone has an idea, I think that would be very interesting. And lastly, to conclude, I'd like to make this point, which is, do we need to test GR? Well, we expect it to fail deep in the black hole interior, but there's no reason to expect a breakdown outside. However, the Kerr prediction has never been directly tested with high precision, and it underlies a huge amount of astrophysics while also playing a driving role in theoretical physics and many questions at the cutting edge of high energy theory. So it's good science to directly test important assumptions that impact multiple fields, and a real test has to have the possibility of changing minds. In other words, it has to be possible to be surprised. And I think this test does that, because if you see a ring and it does not have the shape predicted by GR, then you know that GR is wrong. And this is a very sharp test. So thank you for listening. And since I'm the last person to speak, I'd also like to give a special thanks to the Scientific Organizing Committee for putting together what has been a very exciting conference. And lastly, on a personal note, I'd like to also thank everyone affiliated with the BHI for creating this fantastically stimulating intellectual community. And I've really enjoyed being a part of it over the last few years. Thank you.
So thanks. Let's thank Alex. Okay, Avi.
So Alex, can you conceive a scenario where the LIGO results would be fully consistent with GR, but the photon ring will not? I mean, after all, it's coming from farther out, so.
Yeah, so my understanding of what LIGO does is that they're effectively also fitting a template with some small number of parameters. I think they also have 3 parameters to waveform. So it's the same kind of test. I think LIGO has reported a precision using the same kind of reasoning. Take this functional form and fit it take a functional form for your template and fit it to an observed waveform. And I think by the same type of logic, they've claimed a precision of about 4%. I expect that in the future, when we have improvements of LIGO and LISA and the Einstein telescope and all these other extensions, you know, I'm sure they'll be able to also have very stringent tests. And obviously, I believe GR is correct, and we should all agree with the GR predictions. But that still means that doesn't mean we shouldn't test the theory in the strong field regime where it's never been tested. And I should also add, I think this is never going to compete with gravitational wave tests, but I view this very much as a complementary effort because, you know, with gravitational waves, you're probing, yes, the strong field regime, but also a dynamical merger regime is very messy and different from the pristine environment of a single black hole where you time average over a very long time. This is like another window. They're both in the strong field regime, but they're sort of different windows. One is dynamical and the other is very static and pristine. So I think we should do it all. And the order of magnitude for, you know, in cost for this kind of experiment, it's probably on the order of hundreds of millions of dollars, but still much cheaper than all these other exciting gravitational wave measurements. So I think there's room for everything.
Thank you.
Gary?
Hi, very interesting talk. I just mentioned apropos the last part of your talk that I was involved in one of the 4 flagship mission studies commissioned by NASA and the National Academy called the Origin Space Telescope. And we designed into it the capability to carry a 230 gigahertz receiver. It's a 6-meter telescope at L2, 120 Earth diameters from Earth, and without modifying the design, we could incorporate the hardware needed to act as a distant node in extremely long baseline interferometry with ALMA, for example. So if that interests people, I suggest that they contact Fiona Harrison and Rob Kennicott, who are leading the decadal study report, and let them know of your interest.
I think that sounds hugely exciting. I also think there's room for an incremental approach where it could be, I think it's quite likely that in the next few years, we'll be able to see the n=1 photon ring, maybe even from Earth, using either the autocorrelation approach that Shahar discussed, or maybe slightly higher frequencies, or, you know, it seems like we may be pretty close to seeing it. I think by going to Earth-Moon distances, we'll then be able to see the n=2 ring. And then if we do that, then I think obviously we should also try and go to the Lagrange point L2 and see the n=3. And if you start to be able to see multiple rings, then you can actually compare their widths and start to be a lot more ambitious than just seeing the shape of the ring, but also trying to measure the Lyapunov exponent at every angle around the ring by comparing the demagnification, the angle-dependent demagnification. So I think this might just get experimentally very hard, and maybe to be safe and to convince people that it's worth embarking on this path, maybe we should do n=1, n=2, n=3. But I think all of this is exciting. And once you start to see many of them, you can start to be very ambitious with the kind of science that you do.
The only thing I'll add is that the Origin Space Telescope has a very ambitious science program that fills 365 days of the year already. So this would be a built-in, ready-to-go add-on. And it's a fairly large aperture by space standards. So it's one advantage that it's mission ready if selected to do this.
That sounds very exciting.
Okay, Andy?
So I had two questions. The first one, so in LIGO, I mean, in their numerical simulations, they have 2 incoming Kerr black holes. You know, if you look at the geometry, they're spinning black holes that are described by the Kerr metric, and 1 outgoing Kerr black hole. Do you think that constitutes a measurement of verification of the Kerr solution? You made the statement that the curve, there'd been no measurement.
No, I think LIGO has started to probe the strong field regime and to test the Kerr hypothesis, but I think in their own papers, they claim a test at the 4% precision level, which is very good. And with future improvements, they'll be able to do better.
4% measurement. The question that there doesn't seem to be a clear consensus on is whether the Kerr metric has been tested to some level, and it seems to me that it has been.
I think to some level, but I
some level
to give a very careful.
Can I make a comment, Alex?
Yeah, go for it.
I mean, there, after the LIGO thing came out, there was a paper that generated some publicity showing how, they were only really testing that there's a light ring and not an event horizon. And, the idea is they're sort of seeing that very tiny masses behave like you expect from GR. They go around each other and make gravitational waves as you expect. But I don't think you can really say they've tested that it's a Kerr black hole. Just there's no, what they're trying to do with Kerr tests now is look at something like find quasi-normal modes in the ring down and check that the ratio of two quasi-normal modes is what you expect from Kerr. A number that you can say Kerr predicted this and we measured it.
Okay.
Okay. I have another question. So this thing was supposed to be measured to 0.04%. So that's at least, I don't know what the figures are, but that's at least 100 times better resolution than the EHT had, right? There's no spatial resolution in their thing that's better than 4%, or that would be maybe even more than 100 times. And so would you say that the reason you're able to, it's just the usual thing, you're spending 10 times as much money and getting 100 times the resolution, or is there some magic bullet there?
Well, so you're right that we're going after a very fine feature. So just to bring this to light, the diameter of the ring is about 40 microarc seconds. And here, when we're sampling the change in the diameter as you go around the ring, notice that the variation on the y-axis is between 38 and 38.4 microarc seconds. So we really are going after a very minute variation in the shape of this ring. And I'm not sure if I'm interpreting your question exactly the way you're hoping me to, but I think the magic at work here is this insight that on short baselines, what you see from Earth, which is so these are the data points from the EHT measurements, you're sensitive to all the details of the astrophysical source. But by going to long baselines, you can really narrow in, once you average away fluctuations, you can really narrow in on the very sharp permanent features of the image, which are this ring. And so what a lot of the precision derives from is the fact that we have this ringing pattern. And so if you can see many of these oscillations, you can very precisely infer the period of the oscillation and therefore the diameter of the ring at each angle. So I hope this answers the question. I think the intuition is we are going after a fine feature, but it's really this powerful, we're aided by the existence of this universal interferometric signature on long baselines, which basically washes out all the details of the astrophysical source that you're very sensitive to from Earth, but once you go to space, all that washes out and you're really only seeing this clean ringing. And we're only after the diameter of the ringing. So because we have a simple signal and we're going after a simple feature of it, we get a lot more power.
Okay, Maciek?
Hi, Alex. That was very nice. You you know, I am a great fan of this approach. You got me worried a bit by saying that there are multiple groups working on more sophisticated source models, but I will ask you later about it. I have to.
Maciek may be part of it.
I'm the like other group. Okay. I have two questions really. One question is, do you recall what is the maximal eccentricity of this ellipse that you are fitting? It seems that it should be very close to circular under the assumptions on inclinations that you make. And the second question follows from that. If that's the case, in case that is the case, isn't that kind of more of a test of axisymmetry of space-time more than specifically Kerr space-time? Because you would get, you know, maybe slightly different radii of those rings, but you don't get the radius very well. You don't get to know the radius very well anyway, because distance to the object is unknown. So I mean, wouldn't any other axisymmetric space-time fit pretty much as well?
Well, okay, let me answer in reverse order. So if you can produce an axisymmetric spacetime that also generates a photon ring with a photon ring substructure in images, I think that would be interesting. I also suspect it may be rather contrived, so then you have to get into the details of your Bayesian priors. Do you expect to be looking at a black hole versus some exotic object? My understanding, although I'm not claiming this is at the level of a theorem, but my understanding is that the objects that we really expect to be out there in the sky, like realistic neutron stars, should not be able to have a photon shell because they would have to be inside the radius of the star, so you wouldn't see this photon ring structure. So I think, you know, we do think we're looking at a black hole. But if you can produce some realistic exotic, well, some candidate for an exotic object that could mimic these signatures, I think that's good to know. And then regarding your first question, we know that the photon rings, the subrings converge to the critical curve, and we've proved, I think I mean, some of this was known before, but you can refer to, I think this paper, we proved that the critical curve is an ellipse to either leading order in the deviation from the axis, or equivalently, or alternatively, to leading order in small spin. So there are two limits in which you know that it's an ellipse. You can prove it analytically for the critical curve and wave your hands and say that it's true for the photon ring. But yeah, I guess if you, but there's this caveat, which I put in here. I think we have to be very careful about making very precise inferences for the black hole parameters from the parameters R1, R2, and phi 0 that appear in the fit. Because again, it's true that the critical curve shape exactly encodes parameters of the black hole. Like, are you looking at it from the spin axis or not? What is its mass and spin? But this critical curve shape, which is known exactly, is not observable. And the photon ring shape is observable, but you can't compute it a priori. And in fact, this plot is showing you the same black hole with the same parameters and same observer inclination, but by varying the details of the astrophysical source, you can get measurements of the n=2 photon ring, which differ from the critical curve shape. The critical curve is the dotted line, and these three other profiles correspond to different astrophysical sources for the same black hole. So the only claim I'm making is that you should see a shape to which you can fit the projective diameter of an ellipse, but I'm not making a precise claim about how to infer from the parameters of this ellipse what the parameters of the black hole are, because that does depend to some degree on the astrophysical source profile. We should be able to put some constraints on mass and spin, but not to 0.04% precision.
Okay, thanks.
Okay, and let's take one last question from Shahar.
Thanks, Alex. So I'm not sure, maybe you told me this in the past, but so regarding the fluctuations that will still allow you to measure this quantity. So what kind of what's more important? Is it the frequency of the fluctuations or the amplitude, or I mean and what kind of parameters for the fluctuations would still allow you to make this measurement? Like I mean, do you have an estimate of that already, or?
Right. So I've been thinking a lot about this question, and that's my current summary of my understanding. I think, roughly speaking, we want to know, in the models that we explored, there was no astrophysical noise and we got smooth profiles. In the real world, if you take a snapshot, there's going to be noise, like in this snapshot. And the question is, what is the true amount of noise in the real world? And I think, unfortunately, our level of understanding of plasma physics and our ability to simulate these systems is not such that we can answer this from first principles. We might just have to go out into the real world and measure it. So I think an obvious thing to do is to try to parameterize our uncertainty by asking, let's add in a random source of fluctuations like we did it in our project, and vary the power spectrum in the fluctuations. And obviously, when there's no power in the fluctuations, this is perfectly smooth and you just get the green curve, which is the exact analytic result. As you increase the amount of noise, you'll start to get something like this. And at this level of fluctuation, you get these slightly messier long baseline signals, but if you average for some time, you can still get the signal. And if you keep adding power to the fluctuations, eventually you get presumably garbage, or it takes forever to get to the clean signal like the black curve. And so I think, that's obviously something that we need to understand, and it may be sufficient to do geometric modeling and add in random fluctuations by hand and try to parameterize this uncertainty. I have this vague sense, I haven't made this precise yet, but I have this vague sense that, the more fluctuations there are, the easier it will be to see the photon ring using autocorrelations maybe, but the harder it will be to do the shape measurement. There might be some kind of conservation of difficulty where, if there aren't too many fluctuations, then it will be hard to see the autocorrelation pattern, but you'll have a clean measurement of the ring. On the other hand, if the fluctuations are huge, it should be much easier to see the autocorrelation pattern, but the shape measurement might be hard. So I think these are, we have two different handles on the same photon ring physics, and I think we should push both of them. And it seems like at least one of them, if not both, should be doable. But there's a lot of details to crank out. I think this is a big enterprise.
Okay, thanks a lot, Alex. Let's give Alex another round of applause. And all our speakers another round of applause, because that is our last speaker. And now we'll wrap up with Avi Loeb with closing remarks.
Thank you, Max. Well, first I wanted to ask Alex, are you in Princeton right now?
No, I'm actually in France.
Oh, okay. Because we are about to get a snowstorm here in Massachusetts, and it's already in New Jersey. So I wanted to get a scoop as to how big it is. Anyway, first,
he's lounging on the Riviera while being both at Princeton and Harvard at the same time.
But I'll think about you fondly, Avi.
Okay. Well, there is some beauty. I'm going to jog tomorrow morning in the snow, actually. Well, first, I wanted to acknowledge how amazing it was to witness the diverse range of work that is being done at the BHI, from astronomy to physics to math to philosophy, mainly by the younger generation. And I wanted to salute our postdocs and students for their exceptional work. It gives me hope that the future will be better than the past. Also, our special thanks to Fabio, Achilles, Martin, and Nicole for coordinating this set of wonderful presentations. And the future indeed is promising to be quite bright, because not only LIGO will be extended, the LIGO-Virgo collaboration experiment will be extended all the way to a third generation, eventually perhaps culminating with an observatory on the moon, perhaps. Also with LISA within a decade or so. And the Event Horizon Telescope and its extensions to space. All of that promises to bring a very bright future to our discussions, because it's just like the era of accelerator physics, where we learn things that are important on fundamental particle physics from data, and we're hoping to do the same with black holes. I would like to say that theory is a bit lagging behind in the sense of not knowing the answers to questions like, what is the nature of singularities? What's the solution for the information paradox? What's the ultimate theory of quantum gravity? That could help us understand what happened before the Big Bang. Those are very basic questions to which we don't have answers as of now. And it looks like a lot of the exciting developments are in the realm of experimental data. And the Black Hole Initiative provides the perfect environment for addressing all of the above, both what the data teaches us, but also perhaps trying to address those fundamental questions in theory. Next year, we hope to secure funding for another period of 3 years until 2025 for the BHI. And that will hopefully enable us to address many of these exciting challenges. Most importantly, we hope to return to campus after summer 2021 and meet each other in person. And until then, I just wanted to ask everyone to stay safe and to send my warmest wishes for the holidays and for a path-breaking 2021, full of new discoveries and important work on the nature of black holes. Thank you all for attending the conference.